Welcome everybody. We are here for the ZagDay 2021, an event that we organized in memoriam of Gianluigi Zanetti, who was the past director of Data Intensive Computing at CRS4. Dico anche in italiano, benvenuti a questo evento. Memoria di Gianluigi Zanetti, che è direttore di Data Intensive Computing a CRS4. Io sono Enrico Gobbetti, appunto amico e collega di Gianluigi. Diciamo, farò una brevissima introduzione alla giornata oggi, ricordandovi che la mattinata sarà in inglese, dedicata a temi scientifici, quindi diciamo dopo questo piccolo diciamo inizio in italiano passeremo alle parti inglesi e poi riprenderemo in italiano per il pomeriggio. Okay, I return to English now for the people which are connected abroad and for the non-Italian speakers in the room. I am Enrico Gobbetti, a friend and colleague of Gianluigi, and we have organized this event in a very informal way, in a way that we think would have been loved by Zag, Gianluigi today. The people here that will talk are all colleagues of Gianluigi and friends of Gianluigi, and we organized the day so that in the morning we have scientific talks on areas where Gianluigi worked most of the time with the people that you will hear, and where things are very interesting and have been also moving out. In the afternoon, we will have later on other talks on areas which are more related to application. Before going to this part of the event, we have a very short introduction by the current president of CRS4, Jaime Cao, and by Francesco Mola, who is the director of the University of Cagliari, who will welcome you to this room. We start with Jaime, that will take the floor now, and we'll talk a bit about Gianluigi, CRS4, and why it's important to have such an event. Jaime, please come here.
Buongiorno a tutti, benvenuti a questo workshop in memoria di Gianluigi Zanetti, Zag per tutti gli amici. Un saluto cordialissimo a tutte le autorità civili, militari e religiose che fossero presenti anche da remoto. Un ringraziamento particolare al rettore dell'Università di Cagliari, Francesco Mola, per essere presente a testimonianza, io credo, dell'importanza che riveste il rapporto tra l'università e il CRS4 sul territorio. Ringrazio naturalmente tutti i partecipanti e in particolare ringrazio gli speaker che si sono resi disponibili a presentare un talk, a fare una presentazione in ricordo di Gianluigi. Enrico è entrato nel merito e lo farà in modo ancora più dettagliato del programma e quindi non aggiungo mezza parola in più. But since we have foreigners, let me switch into English for this morning. It looks like that the same operation is going to be done in the afternoon in the opposite direction by switching from English to Italian. So it is, of course, a great pleasure to have you here, particularly. It is a great pleasure, and I would like to thank you so much. I would like to thank so much the speakers for the availability to present their talks during this event, during this workshop in Zag's memory. You know, CRS4 has been established in 1990, so 30 years ago, by the regional government to become a leading research and development center in computation and information technologies, at least at the national level. His first president was Carlo Rubbia, and who was followed by very well-known scientists like Nicola Cabibbo and Paolo Zanella, who has been also the CEO when Carlo Rubbia was the legal representative, the very first legal representative. I could say that tremendous results have been obtained so far by CRS4. We have got the first Italian website in 1993, the first online newspapers in 1994, the first simulation of two-phase fluids in 1994 again. And thanks to ZAG's activity, for example, we have been able to have the first Italian school online in 1994 again, first webmail in 1995, first Italian search engine in 1995 again, first personalized medical simulation of blood flow in 1999, first multilingual geographical information system in Italy in 2000, year 2000. We have been designing in 2002 experiments for the International Space Station. We have been the recipients of the ENI Technology Award for the reconstruction and regularization of seismic data in 2003. We have in 2004 the first medium-sized Linux clusters based on 64 bits. We also have a DNA sequencing of 1,200 Sardinians published on Science in 2013. We have been documenting and presenting to the public a large and unique collection of prehistoric statues of the Monte Prama complex in 2013. And particularly this result was to be given to the group led by Enrico Gobetti. We started in 2014 a strong collaboration with Luna Rossa Prada Pirelli team, which is still going on. We had in 2015 a paper together with Francesco Cucca, a very well-known scientist in Sardinia, published on nature genetics. The paper was related to genome-wide association analysis based on the whole genome sequencing in Sardinia. We had the largest next generation sequencing core facility available in Italy in 2016 with 10 terabytes per month throughput. I would like also to recognize the activity that was performed with the portable system rapid ELT for emergency solution that we have been using in Rigopiano in the last years. And in 2017. Finally, I would like to mention the activity we have been doing for the interactive model of Nuraghe Genna Maria. I strongly suggested the foreigners, the hosting that we are hosting these days to have the chance to take a look at this Nuraghi that are really quite interesting from the historical point of view. So it looks like that the goal the regional government had in mind at the time when CRS4 was established has been reached, I would say, with honor and recognition. I had the opportunity to become a consultant for CRS4 back in 1998. And I quitted this position in 2015 before receiving last July, the appointment as the sole administrator of CRS4. And therefore, I had the honor to meet Zag a long time ago. I had also the possibility to meet Zag and his wife sitting here in front of me when buy things for surviving at the supermarket. That was done many times, actually. We had the opportunity to, exchange ideas very quickly, buying pasta and many other things. So, Zag, let me call him Zag because we know him as Zag, and he is Zag for everybody. So he has been the director of data intensive computing. He held a degree in physics from the University of Bologna, 1984, and a PhD in physics from the University of Chicago, 1988. So he has been joining CRS4 in 1991, and before that occasion, he had the chance to be serving as a teacher at Princeton, Los Alamos, and the Ecole Normale Supérieure. So his research activities are, very, very broad. He has been touching many areas: computational science, statistical mechanical, mesoscale computational techniques, fluid dynamics, simulation, very many. In recent years, the major focus was on the development of strategies and infrastructure for data-intensive application, able to guarantee the processing and analysis of massive and complex heterogeneous data sets. Zag's activity has been resulting in a wide number of publications, as you know, in major scientific journals and conferences. Actually, these activities have found many practical applications that have been transferred to clinical and industrial practice. Unfortunately, Zag suddenly died 2 years ago. We have lost a great man, I would like to say, and I would like to emphasize. We have lost a great researcher, and we have lost one of our directors. So it is an honor and a privilege to dedicate this workshop to his memory. Let me introduce then the rector of our university, Professor Francesco Mola. Please, Francesco.
Good morning, dear Benedetta, and also dear Davide, Ilaria, and Matilde, and dear all. Good morning to Jaime and Enrico. Thanks for inviting me in this very particular day. My speech will be short, very short. I have the opportunity in the afternoon to have time for other things. And it's a genuine greeting to an event that brings us together, but at the same time to an event that none of us have ever wanted to attend, at least not without Gianluigi. My address speech is on behalf of the whole academic community of the University of Cagliari, not only on behalf of the researchers who worked with Gianluigi. There are many research topics that Gianluigi has considered in his research activities. So there are necessarily many people from our university that he met and interacted with him. It's certainly an important day for the people who met Gianluigi. Everyone considers that someone can leave us, but no one is ready to accept it, mainly when it happens prematurely. I remember we discussed with Annalisa Bonfiglio and Enrico Gobetti the importance that CRS4 would organize something to commemorate Gianluigi. We never imagined what would happen in the next few months, the pandemic. And researchers of all countries and institutions have continued their activities trying to react to this terrible situation. A huge effort has been made in the academic world and the non-academic world, not only in the teaching domain, but also in the scientific divulgation domain. History will tell us the consequences of this effort and how much we have contributed to mitigating the damage. But indeed, one thing that everyone lacks is the chance to meet, to work together, to exchange their experiences. Gianluigi worked so much with data. He knew the importance of the correct data treatment, data wrongly and the importance of the right data modelization. I'm sure in the many discussions with colleagues, in the many activities related to the analysis of data on COVID-19, Gianluigi would have been a protagonist and would have given his essential contribution. Many researchers have contributed to analyze data related to the pandemic, disseminating knowledge and correctly interpreting the data. It demonstrates how important the issues related to some disciplines are for the progress of humanity. At the same time, we have seen many incorrect interpretations of the data and the results of the applied models. Even more, this must push our communities, academic and non-academic, into dissemination operation and strive more and more to attract young researchers to some topics. Working with the young people has always been very important for Gianluigi. We used to talk about the importance of training and research. Gianluigi pushed hard for activities in our PhD programs, and CNRS4 has grants for some of our PhD programs. I am lucky because I met Gianluigi not directly for research reasons. With Benedetta and Gianluigi, we shared some experiences as parents of our children. And I remember it was a Sunday, I think in 2003 or 2004, during a lunch, in reality, during a break of a typical Sardinian lunch in the country, that we talked about our research interests. And I immediately perceived how much passion he had for the things he did. And I remember that we discussed our experiences abroad on common research topics. In short, a real surprise for me. And I also remember that we talked about the importance of a stronger interaction between the University of Cagliari and the CNRS4. It may be that in the next few years, Jaime, we will be able to do something more structured. Let me conclude by saying that I like very much how this event has been organized. A scientific part and a more personal part. Precisely the two aspects of Gianluigi that have impressed us all. Good conference to all. Thanks, Gianluigi, for sharing some moments with me. I am honored to have met you. Ciao, Zag.
Okay. Thanks, everybody. As you've seen, it's not easy for us to talk from here about Zag, but we try to do something that should be uplifting, in the sense that what remains is the people you have met, the things you have done, and for people like Zag and things like that, you mix the two. No, you talk about scientific things to people that don't care, or to people that cares, and so on, because you are passionate. So the event, I will start quickly. From this short introduction, we move to the scientific part immediately. There will be two sessions this morning. The first session is on computational modeling and simulation, which was the focus of basically the first part of the career of Gianluigi, with I think exceptional talks about these topics that you will definitely enjoy. And then we have a coffee break, and after the coffee break we will move to the second part of the interest of Gianluigi. Not that we won't cover everything on data intensive computing and scalable data analysis, where we will have 3 talks on how you can make the most about the data you have to the benefit of everyone. The talks will be asked to the people to do talks that cover the scientific aspects, to know how important these aspects is, and all the speakers will also talk about the joy of doing these things together with Zag. So let's move to this scientific part. I welcome here Giorgio Fotia, who will be the chair of the first session on computational modeling and simulation, and he will introduce the speakers. Thanks again. Welcome, Giorgio.
Good morning to everyone. I'm Giorgio Fotia, friend and colleague of Gianluigi. I've been knowing Gianluigi since the very beginning at CRS4, because we both arrived at CRS4 in 1992. And well, I do remember Gianluigi as occupying on that day in computational modeling and simulation. So it's now a pleasure to introduce Alfio Quarteroni, which is one of the 2 speakers of the session. Alfio is now a professor of numerical analysis at Politecnico of Milano, and emeritus at EPFL, the Federal Institute of Technology of Lausanne. He was previously researcher at CNRS, professor at University of Minneapolis, and then scientific director of CRS4. He has been awarded of very many prizes. He's member of a European Academy of Science, Italian Academy of Science, Lisbon Academy of Science. He was awarded, among many other prizes, of the International Galilei Prize for Science and of the Galileo and doctorate honoris causa in naval engineering. He is the author of more than 25 books and hundreds of papers. His papers are published in conference and international journals, where also he has an intense editorial activity. His many interests are in mathematical modeling, numerical analysis, and scientific computing, with application in fluid mechanics, medicines, and improvement of sport performances. His group at the PFL was responsible of the mathematical simulation and optimization of performance for the Alinghi in the America's Cup. And so now I would like everyone to join me in welcoming Alfio in speaking on mathematical models for Earth and circulation.
Thank you very much, Giorgio, for this very nice introduction. Let me see if I can first share my screen. I hope you can see it. Can you just confirm me that you are seeing it? Can you hear me?
Yes.
Okay, can you see my screen?
Yes.
Okay, thank you very much. So thank you very much for inviting me. I'm very proud to be here. In this day, it's a very emotional day. And thank you for organizing this very important event. So I'd like to give this short presentation. I will try to skip all the technical detail. As you see, the presentation is to see with mathematics, with a physics-based model of the heart. And I'm glad to start with a paper, and a paper that shows how and when this story began, actually, and it began at CRS4. He began in Series 4, and Gianluigi has a role in that. We met in the mid-90s. Massimiliano Tuveri, who was at that time a young doctor at the Bronx Hospital in Cagliari. And Massimiliano came with an interesting subject, and he wanted us to address. And Gianluigi was one of the very first who took this issue. And we had very long and useful discussions on that. And we started basically there. And for me, this was absolutely a premiere. I mean, this was the very first time where I started working on this topic. And a few years later, we wrote this paper. We still one of the reference papers in the field. And as you see in the acknowledgements, Gianluigi is of course acknowledged, as well as Luca Formaggi at that time. He was at Series 4, and Andrea Giacchetti, another Series 4 scientist in that time, say. And I have to say that I tried to convince Gianluigi to be a co-author, and I insisted, and Gianluigi did not accept that. And I think this was for his generosity. I mean, he, of course, he was not the one behind the writing and many of the development of the papers, but certainly was one of the, say, people who inspired this research. And again, this is a sign of really his being, his attitude and his character. So now, let me also take from one of these, say, the pages of this paper, this picture, which is on the homepage of the ZagDay today. I guess this very picture. So this was one of the very first pictures that we elaborated Series 4, we computed Series 4, and it's showing a two-dimensional analysis of a carotid bifurcation. So this is really one of the landmark pictures that we used many times, and it has a very strong imprinting at Series 4. Today, where are we today? Okay, I will just give you an idea of what has been the development and how far we have been able to move this research. And today we are addressing the full heart. I guess all of you have an idea of a rough idea or a detailed idea on the way the heart works. The heart is a 4-chamber organ, and it intakes venous blood. It's sent it to the lungs, and then the oxygenated blood returns to the heart, to the left part of the heart, to the left atrium, to the left ventricle. And then it pumps through the aortic valve this blood into the main aorta, and from there it reaches all the part of our body. So it's an incredible organ. It's very small, almost completely empty, but extremely powerful. And it works because at every instant we have an electrical stimuli that starts automatically. So we do not have to do anything for that, fortunately. So the stimuli originates at the sinoatrial node. It propagates into the sinoventricular node, and from there through this very, say, sophisticated highway system, it is propagated to the whole muscle, to the whole myocardium, and it reaches every single cell. And there is a kind of miraculous generation of force, what is called the active force, which is induced by the electrical stimuli, say. And this eventually will determine the compression and relaxation of the heart, and therefore the fluid dynamics inside the heart and the ejection of blood, and therefore the, say, the supply of blood and all the nutrients to all the cells of our body. This is a very long story that I made very, very short, and the idea is try to translate the whole process into mathematics. I will not give any equation, but the equations are behind the screen, say. And here you have the mathematical model, say. The mathematical model, which is a set of coupled little boxes or little circles. Every little circle is encompassing and coding specific activity like the electrophysiology, which is the propagation of the electrical field, the active and passive mechanics, the mechanics that activate every single cardiomyofilament, the passive mechanism that is responsible for the compression and dilation of the heart, the fluid dynamics, the perfusion of the heart itself or the muscle itself, thanks to the coronaries, the activity of the valves, the relation with the external circulation and with metabolism. So this is what mathematicians call a complex coupled system of partial differential equations, and they are non-linear and they are fully coupled because everything depends on everything else. So this is a very compact and sketchy picture of the whole story. So provided we can solve the equations that are behind these little circles, we will be able, in principle, to reproduce the heart activity. And this is our goal, say. And the goal is to end up with having, say, the electrophysiology, for instance. What you see here is a real heart. You see the propagation of the electrical field. You see the colors. Those are the effect of the numerical simulation. You see the voltage in millivolt of the atria and of the ventricles. You see the propagating front, the electrical propagating front. Basically, behind there are the Maxwell equations, and from that, from this type of simulation, doctors can have a complete picture of the electrophysiology. And of course, this can be used to have a better knowledge or more quantitative knowledge of what's going on in our heart, but also to have doctors in operating. This is one example. This is a research that is carried out together with the San Raffaele Hospital in Milan. This is a heart which is affected by, say, scars because of a previous infarct. Now we want to reconstruct the biomarkers. Biomarkers basically mean the characterization of the, say, imperfect or pathological rhythm, electrical rhythm of the heart. And at the end, we would like to end up with indicating points, which are those that you see on the right-hand side of the picture, points where the doctors have to operate, and more precisely have to ablate. Ablation means using a catheter entering into the heart and burning the tissue in order to prevent these irregular pathways to propagate, say. So this is a very, say, experience-based activity. It takes several hours in the operating room, and our dream or aim is to try to help doctors to better locate these points and to ablate as little as possible. So we are not only there to try to better understand the physiology, we also want to help the doctors to take better actions while operating. Of course, the electrophysiology is the trigger of the mechanics, and this is a beating heart. And this is the very first time that I show this 4-chamber heart, which is beating. So I'm really glad to show it here at CS4 for the first time. This is non-published yet, but it's just a proof of what you can do with the mathematics. Having a beating heart, which is hopefully realistically beating, in the sense that all the quantity or the physical quantities that you're seeing here are reproduced correctly. Sorry. So this is the electromechanical activity. We are coupling the electrophysiology with the mechanics. And what you see here is on the left-hand side is the calcium concentration, and on the right-hand side is the modulus of the displacement. So you go up to 2 centimeters of displacement, which is the one associated with the red points. And of course, below you have more quantitative pictures. This is a PV loop, which is very much used at the clinical level to assess the good behavior of an heart, say. Then you can move to the internal part of the heart and to the chambers, where you have equations that describe the fluid dynamics. You have blood inside, and blood is flowing into and out of the heart. So what you see here is the left heart, meaning say the atrium, the left atrium, with a pulmonary vein that supply the left atrium with oxygenated blood coming from the lungs. Then you have the mitral valve, this one, which connects the atrium and the ventricle, and then you have the aortic valve, which connects the ventricle with the ascending aorta. So what you see here is the velocity field on the left-hand side, the pressure at the centrum, and on the right-hand side, say, the vertical structure that is created inside our left heart. So you may, I hope, appreciate how complex is this fluid dynamics, and you can guess how difficult it is to try to reproduce it by mathematical methods and numerical simulations, say. And just to give you an idea, this will take order of a couple of days on one of the biggest supercomputers in Europe, just to reproduce a single heartbeat, namely one single, second of real life. Of course, you have to connect the whole thing, the whole heart to the rest of the circulation, because heart is not living in the middle of nowhere. And to reproduce the behavior of the whole circulation, we use electrical circuit analogy. So this, mathematically speaking, translates into a series of a system of ordinary differential equations. And when you have the whole thing together, you can then have what you call a multiscale simulation of the heart by connecting the three-dimensional analysis of the heart with what we call the zero-dimensional analysis, because you have only dependence on the time variable and not on the space variable for the rest of the circulation. Again, you can use this for investigating healthy and unhealthy situations. On the right-hand side, you have a heart where you have mitral regurgitation. This means that the mitral valve does not close perfectly well, and therefore there is an incorrect flux from the ventricle back into the atrium, and this is very critical and deserves to be investigated, because, you know, in some critical cases, this will call for an operation to replace or to fix the mitral valve. So we are really behind the scene, the clinical scene. We try to help doctors to take the right decisions, even when these decisions concern surgical operations. Of course, this is a work that involves many people, and I'm glad to show at least quickly the pictures of the IR team, which are mostly based in Milano or in Lausanne or in Houston, say. Really sorry. I'd like to make another little snapshot of research that we started at CNRS, nothing to see with the heart. This has to see with the seismic wave propagation. And Professor Kaus mentioned this activity in his very general introduction. You see there is an affiliation here again with CNRS. This is a 1997 paper that I was still at CNRS together with Fabio Maggio. And this is a collaboration with some, engineers from Politecnico Milano. We started from there with this research. And so the very first code that we developed was code made at CNRS. And now we have been developing this, and we use it for try to predict the outcome of future possible earthquake scenarios. Just to give one single example out of the very many we investigated, this is the area of the Marmara Sea near Istanbul, and that's a very critical area because this is a very long fault, and we know that we don't know when earthquake will occur, but we know where earthquakes will occur, and this is due to the this is basically, say, a result of consequence of the presence of faults, and the magnitude is also predictable because it depends on the size of the fault, on the length of the fault. This is a very long fault. You see, it's 90 kilometers long, so we are expecting say earthquakes on the magnitude of the order of 8 in the Richter scale. So this is the simulation. It's a simulation that involves about 500 million unknowns or degrees of freedom, and you can describe different scenarios depending upon the way the fault will be rupturing. If it's a bilateral rupture, directive rupture, so east to west or west to east, and see the impact that you have on the metropolis, which is a very intensely populated metropolis. So we use this type of simulations to predict the risk and to try to hopefully help the governance to take the right actions minimize the risk. There was a very, repeated reference to data in the previous presentations. And this is another landmark story of Series 4, and Gianluigi has had really very important and I would say determinant role in that. Today, talking about data implicitly means talking about, machine learning, at least in the field of scientific computing. And the machine learning can be regarded as an alternative way to physics-based models, those that have been addressing until now. And I'd like to just to give a very quick hint on the way, the two words, the two approaches, the one based on machine learning and data analysis, the other one based on physical models, can indeed cooperate and producing extra value. So I still took this snapshot from the homepage of the ZagDay, and this is a cover you see on Data Deluge and its application by Gianluigi again. And well, where are data? Where are data that are, fundamental to feed the models? Well, in the previous analysis, data are those that come from the clinical practice, as everybody knows at Series 4, because it is a very long tradition and collaboration with the medical environment for data acquisition. So there are CT scan, there are CNMRI, there are LGE MRI, and we use them to reconstruct the shape of the heart, for instance, and the boundary conditions. We use them to create what is called the grid, namely to the partition of the geometry into little small pieces with a regular geometrical shape like tetrahedra or hexahedra. Like in this case, we're using order of 60 million hexahedra to reproduce, say, just the myocardium of the heart. So data are very essential also for physics-based models. Data are essential, of course, for seismic wave analysis, because we know that, well, I took this picture is a bit, outdated. It's from 2016, but situation is pretty much similar today. You see the way the big catastrophic events are distributed along all across the planet, and you can say that this is unfortunately very democratic attitude, right? You have geophysical events like earthquakes, tsunami, or volcanic activity, which are marked in red, and you have meteorological events like tropical storms or floods, mass movements, or drought, wildfire, extreme temperature, which are distributed everywhere. In particular, the role of the seismic activity is extremely important, and this is a map that tells you why it's so important to try to combine data analysis and physics-based models. These are the distance from the hypocenter, right, for the source of the earthquake in terms of kilometers. And this is the magnitude. And those are the availability of data, depending upon the distance from the source and depending upon the magnitude. And as you see, you have many more data very far away, but very few data near the source, and especially when the magnitude is very high. That's why it's so important to couple data, statistics or data analysis with models, which surrogate information on data when data are not available for obvious reasons. Now, this is a kind of conceptual map. I've been talking about physics-based model, and this is reproduced in the upper part of my slide. And I've been talking about data analysis, which is in the lower part of my slide. So in the upper part, you start from data, very few data. You have models that are based on physical principles, the basic Newton's law, Schrödinger equations, Maxwell equations, Navier-Stokes equations, so on and so forth. And then you get the solution. While here, when you say artificial intelligence or machine learning, artificial neural net, which is a way to empower artificial intelligence and machine learning in particular, you have training data. You train your network by data, and then when you have a new data, you use your previously trained network to produce the new output. So in principle, you can regard these two parts of the story as a completely independent. You have people working only on the upper part, people working on the lower part, sometimes in a kind of dogmatic way, okay? Try to convey the message that this is a wrong attitude. I'd like to really say stimulate people to work at the interface between the two approaches. So let me just give you another example where we have been using data ourselves, and it's a completely different type of application. See, this has to see with sport. So you have infinitely many examples that you can provide. So this is a match from the last championship in the Serie A. This is this is Juventus versus Sampdoria, and you see for every single match you have generation of very many data. You have 22 cameras that are following the players on the field, and at the end of the match you have order of 10 million of data only for the positional information on the player. And we use this here, an algorithm that is called the virtual coach, which is actually available to every coach in the Serie A, Italian Serie A, and this algorithm, this platform actually, this software is capable of producing real-time information about the setting and the possible variation changing in setting on the terrain for the coaches. This has been developed at Math and Sport, which is say company that has originated from Maxoff, which is a spin-off company, Politecnico Milano, and it was also used recently from the volley team in the European Championship. You know that the women have been winning the last championship. This was a week ago or so, and we use it for preparing the match, and also for during the match to change the position of the athletes and change the tactic and the strategy. And this is real time, and this requires having a very sophisticated algorithms from one side, but matching this with the capability of elaborating implementing those algorithms on very fast local or say remote supercomputers in order for the coaches to have this available in real time. So this is one of the billions of examples where we show that the data are actually having an overwhelming role in our activity every day. And let me conclude by saying that my way to see the way the physics-based models and the machine learning algorithms, which are based on data analysis, can cooperate. So you have two modes, which are called standalone mode. Physics models produce physics-based output, and machine learning algorithms produce data-driven output. And the two worlds can continue to proceed independently. We already have cooperative modes where we use physics-based models to regularize machine learning algorithms, to augment the data set, the training set, by means of numerical simulation. So in this way, you see the physics-based models as a support for machine learning, and you have data-driven output, which is enhanced by physical knowledge. That's one way. Of course, there's another way, which is this one, right? Use machine learning algorithms to uncover, to reveal constitutive laws of new materials, for instance, to accelerate the multiscale problems, to build, reduce order models to make physics-based models more, much faster, and therefore much more interesting. And this is what we use in the clinical practice already. But then you have a more genuine way to have a cooperation. And you can use physics-informed neural networks. We really try to combine the physical knowledge. You are, after all, investigating a specific framework, a specific physical event, a social event, an economical event. You want to take advantage of that and to use it to generate new algorithms, new approaches, new mathematical approaches that create new knowledge, I would say. As you see, I will not enter into these details, but you already see the way science can take advantage of knowledge from both sides. It's not time of separation. It's not time of developing a dogmatic parochial knowledge here. is the time to take advantage of the new era of data, of the big data, and try to take advantage of them while developing new physics-based algorithms. And on their side, so using physics-based algorithms to enhance the powerful of data analysis, of machine learning algorithms. And I think CRS4 is perfectly placed for that. CRS4, those two cultures are there since the very beginning. And let me just conclude by saying that Gianluigi would be a perfect actor in moving ahead and moving forward this type of new knowledge and new culture. And by that, I would like to stop, and I would like to thank you for again giving me the opportunity of talking to you this morning and being here for this very important and emotional day. Thank you very much.
Thank you, Alfio, for this vibrant and interesting presentation. I wonder if there are some questions, comments. There is one question from Stéphane.
Alfio, thank you for the wonderful talk, really stimulating. I think Gianluigi would have been enthusiastic about pursuing the work on neural networks. And however, I wanted to ask you a question. As a mathematicians, wouldn't you agree that the neural networks have been somewhat hyped, especially in classical physics applications, fluid mechanical applications? After all, if you want to know whether a system is continuous and deterministic, it's a simple mathematical problem from the data to see whether the data lie in some submanifold of the space of data. Detecting whether locally you are in a lower dimensional submanifold does not require a lot of computation cleverness. It's relatively easy.
Thank you, Stéphane. Yeah, you are absolutely right. I mean, there is a fantastic contribution from the convolutional neural network, of deep neural network, to try to better assess the quality, the behavior of the regime of flow, complex flows. While you certainly know the work of Stéphane Mallat and many others in this respect, I really believe that when I say we, I mean myself and the people who have been more trained from, say, some decades ago in physics-based knowledge, we have to be extremely open to that because it's really fresh culture, fresh knowledge, and new knowledge that can really complement our own knowledge. And my recommendation, especially for young people, is to be very open-minded because independently on the way they have been trained, this is a great, I mean, this era offers great opportunities to be embedded by this culture that come from different environments, but they play on the same terrain, on the same scientific ground. So thank you very much for this comment, which is absolutely appropriate and very sharp.
Thank you, Stéphane. Thank you, Alfio, for the answer. Are there questions, other comments? One, the back.
Thank you for a wonderful and inspiring talk. This is Petr Holub from BioImage. I wonder, have you looked into explainability of those neural network models? If there is any way to map those models to the physics using the explainability tooling, explainability techniques that have been developed in the last, say, 5 years, where you can look inside the neural networks or analyze its behavior based on, say, experimenting with the network and understanding on what it reacts, so that you can find if the neural network is basically behaving in a physically sound manner.
Thank you for your question. That's a very tough question, I have to say. Let me try to provide an answer on the basis of what I've been understanding so far. from mathematical perspective. So I'm a mathematician, so I try to see things from a mathematical perspective. What I see is that there is a very important activity to better understand why neural networks work and why sometimes they don't work. When you come from the physics-based models and you come from the realm of mathematical models and numerical analysis, you have tools, you have theoretical tools that guide you to select the algorithms and then to assess the quality of the algorithms. You have error analysis or recall error analysis. We try to predict, even before making the computation, whether or not you should expect a good result and estimate the error, even though you do not know the exact solution. So this is still somehow missing in the neural network framework, say. And I'm taking the picture as of today, and I'm sure that in 1 year from now, the situation will already be different because it's a rapidly evolving field. So what is the what are mathematicians trying to do right now? They try to investigate basically two different kind of, I'm oversimplifying, of course, because of time, shortage of time. Two aspects, at least two aspects. One is about approximability. You call explainability, and me call it approximability. Is a bit different indeed. What I have in mind, approximability means does a neural network have the possibility of reproducing the input-output relationship of any possible physical system? So there are works in this direction. There was made by, at the beginning, by Glencoe, a Russian mathematician, and later by other people, where they try to see the way you can approximate by neural network, depending upon the number of neurons, the number of layers, say, the possibility of approximating virtually any kind of C0 continuous map from the input data to the output data. This is work in progress, but there are already some very important achievements in this respect. And the second one is how to interpret neural network on a physical ground, like Hamilton-Jacobi systems. And this goes back to the very early work of Parisi, who is, as you probably know, a very eminent Italian physicist and actually the president of the Accademia dei Lincei. And Parisi long ago, I'd say 30 years ago already, with the French mathematicians tried to interpret the very first neural networks under the heading of Hamilton-Jacobi system. After all, you are minimizing quantities, you are minimizing functional, you are minimizing Lagrangians. And I think this is that's a very good way to try to inject more physical knowledge into algorithms that very often are only based on, say, developing new minimization algorithms, stochastic minimization algorithms. There is much more hidden behind neural networks, of course, and this deserves to be revealed. This deserves to be, say, better understood, and I'm sure that we will experience very sensational progress in the years to come.
Okay, thank you, Alfio. Are there other questions? If not, I thank again Alfio for his wonderful presentation.
For listening to me.
And move to the second part of this first session. And I would like to invite Stéphane Zaleski, who is to his speech. Stéphane is currently professor at Sorbonne in Paris at the Jean d'Alembert Institute. He took his doctorate in physics at the Ecole Normale Supérieure in Paris. His most interest is on numerical methods for multiphase fluids with application in atomizations, cavitation, porous media flow, and droplets impacts, among many possibilities. We will now speak about challenges in the multiscale analysis of multiphase flow.
Oh, thank you. Dear Mrs. Zanetti, dear Benedetta, dear Ilaria, Matilde and Davide, dear colleagues of CRS4 and authorities, I'm very happy to be here to talk with you, that you invited me for this event. I'm very touched, and there is also some emotion. I recall the first time that Gianluigi told me about CRS4. He says, "Come, I'm in this new wonderful place. Please come here." And I will try to recall both the personal and scientific events that of those days. So the first time I met Gianluigi was at a conference on lattice gas cellular automata. At that time, I had developed something called a lattice gas, which was at the time a very new kind of toy model for what happens when you heat a fluid and it starts moving, like you have some motion in a room around the heaters of the room. And that was the paper. Burgess was a student at MIT. I was at MIT myself. And at the time, Gianluigi was in Chicago. And we met, in fact, at a conference, I think it was in Los Alamos. At that time, that was a very recent development, and I had followed my PhD advisor, Yves Pommeau, who had invented the lattice gases. And in a way, the lattice gases were also invented by Leo Kadanoff, who was the mentor and advisor of Gianluigi. So that's my second point in common with Zag. We both had very famous advisors, which is not very easy, you know, when you think that your advisor is a zillion times more intelligent than you are, it's difficult to start. And Gianluigi had a bit of that problem too. But that's only my second point in common with Zag. The first point in common, that is his name starts with ZA, okay? And as a result, when we wrote our first paper with Kadanoff, he beat me to the last position. So, of course, I was enthusiastic about agreeing to the offer of Kadanoff to work with them. Kadanoff was almost a Nobel Prize. It was very fascinating. So we did this work, which predicted that the Nusselt number, that is a measure of how much heat is transported, goes like the Rayleigh number, a measure of how much you increase the temperature to the power 2/7, which contradicted the classical law raised to the 1/3. There has been a lot of debate about that. Well, we had a wonderful time at that time coming to Chicago and walking in the streets of Hyde Park, which is the area around the University of Chicago, reading books like this. And we managed to avoid most of the lampposts, but maybe not all of them. But we survived. And later, a year later, Gianluigi wrote this paper, which is amazing. It was been cited 2,665 times that I checked yesterday. It was the beginning of a new method for computation called the lattice-Boltzmann method. He wrote it with another student of Kadanoff, Guy McNamara. And it's amazing to have so many citations for a paper you wrote during your PhD. I think it shows Gianluigi's enthusiasm for new methods. And that's why I said he would have been also enthusiastic to continue the development of neural networks. As all the new ideas, it does not necessarily survive forever, and sometimes there's a bit of hype. Lattice-Boltzmann methods had some defects, but we continued at first on that, and with Gianluigi we developed a lattice-Boltzmann method for two-phase flows like air and water, oil and vinegar, etc. And this was this paper, which was also cited many times, but not as much as Gianluigi's original paper on the lattice-Boltzmann method. We started that, we couldn't work in Chicago anymore because I think Gianluigi was at least during part of the work in Princeton. I was in Paris and we worked with Dan Rothman, who was at MIT, but we managed to meet in various places and get this work done. And that was absolutely great. We discovered when he did that work, the so-called spurious current. So I experienced something that maybe a lot of scientists have experienced. You find something weird in your research. You think it's so weird, it's actually a defect. So you don't want to talk about it. So Gianluigi and Dan Rothman and Andrew Gunstensen and I, we fell to this mechanism. We didn't talk about the spurious currents, but we had found them. And then, as I said, there is sometimes some hype in some scientific discoveries. So the two-phase ABM and LBM has the same problems as all lattice-Boltzmann method. It's inaccurate as the velocity is increased, and the Mach number is not negligible. So I developed a two-phase volume of fluid method, or volume or VOF, and during one of my visits to Chicago, which was without Gianluigi, and I told about it to Gianluigi. I gave him the 2D code, and one day I arrived in Cagliari. I saw some really superb results obtained by Gianluigi, very nice movies. And so all that remained to be done was to write the paper, which we did together. And actually, Gianluigi also contributed to some improvements of the method at the time. And we wrote this paper, which is now cited 1,253 times, which is still a lot. And in fact, it's interesting also because this paper is cited less often than the other paper on lattice-Boltzmann, but I think it's a better paper. But it's, of course, citation that don't tell you everything. I'm mentioning the citation to show how impressive Gianluigi was and how famous he was, even when he was very young and a PhD student. I think it's open, you know, it's maybe not necessary to dwell on that, whether Kadanoff considered he was his best PhD student ever. Maybe someone in the room had direct communications with Kadanoff about that. But in fact, it doesn't really matter. What matters is that Gianluigi has this drive. The way he managed to build on the ideas in the paper and put a whole team of many people on the ideas that I had discussed with him to make this happen, to make a great work out of it and a famous work out of it. That was remarkable. He was not just a creator of ideas. He was a creator of ideas, but he was also a doer, someone who could assemble a team, make things happen. He knew it was important to make it happen, so to put a lot of resources into it. And he had this very strong willpower and this very strong working ability. He could stay up all night and don't feel tired after that. I mean, maybe that was only in the 1980s, maybe not a bit later, but he really, it was very useful also because it was very hot in Chicago at the time. There were heat waves. And so it was very useful to be able to stay all night in the computer room instead of going back home where it was too hot. And so he applied this force to this volume of fluid idea. And so here is the first movie. So someone has to push a button to start the movie. Do you have access? Yes. So that's the first movie that Gianluigi showed me at the time. Doesn't seem like much, but it's a droplet falling on a layer of fluid. That was the first time ever that, and then you see the same thing from below. That's the first time ever, and you see the bubbles formed below. So that's the first time ever that this was done in a simulation movie. It was, of course, there were some movies in experiments. In experiments, they don't really see the bubble below, so lots of people ask me questions and so on. This is another movie. okay, of a thin thread of liquid, like the liquid falling from a faucet, decomposing into droplets. So these movies were made by Gianluigi. He not only, with Rubens Cardovelli and Carlo Nardone, he not only wrote the three-dimensional versions of my two-dimensional code, he also found the software for doing the graphics. And he then made the movies with his colleagues, and he engraved them on a laser disc. CRS4 was one of the places that had the first laser discs to record the videos at the time. And I had a lot of trouble reconstructing these movies. They are in some books now, but you have to manipulate the codecs, the video data. It's not obvious. Maybe CRS4 has somewhere stored the laser disc somewhere. Please keep it carefully. It's an important historical thing, so please keep it. So this movie was inserted in Multimedia Fluid Mechanics, which is a CD, a kind of book of movies realized by David Quéré and Marc Frémigier. They were on a contract with Bud Humsey, who is listed as the official author of the book, but they actually, David Quéré and Marc Frémigier and others did the work, and especially David Quéré, who contacted me so that I could send him the movie, but he thinks it's my movie, but in fact it was Zag's movie, okay? And it's a great honor to be in that book because we are the only non-experimental movie in that book. Later on, David Quéré wanted to include it in his book with Pierre-Gilles Degène and Françoise Borchardt-Riard. Françoise Borchardt was against inserting videos. Pierre-Gilles Degène was indifferent. So David Quéré did it. So we are in two books. And David Quéré told me the whole story yesterday. So I have the dates more or less right. So that was in, that happened in around 2005. So that was much later than the actual paper that we wrote and the movies. That was 10 years after the movies were created. At that time, David Quéré told me, I want to insert the movie because it's a historical movie. So 10 years later, it was already history, okay? They made history indeed as one of the first simulations of this thing. But I must say, at the same time, Greater Tryggvason also produced very nice 3D movies of bubbles rising in a channel, but maybe we had the first droplets movies. So we felt at the top of the world. We had a fantastic method to deal with droplets, and we thought CRS4 was the ideal place to make this happen. But it didn't work out that way. We talked to Claudio Bruno, who was a consultant in combustion. He knew the importance of computing droplets correctly for combustion, but we didn't have a huge grant from ESA. Zag participated in a conference with industrialists in Chicago, but he felt that the competition from the American groups was too strong and the American industrialists would give money to American researchers. In my case, it was counterproductive. The industries liked the lattice gas and the lattice Boltzmann so much that they thought they were the same thing, by the way, but I had a contract with them to do lattice gases, so they were upset I was doing volume of fluid, although volume of fluid was much superior. But I pursued the development with Rubens Cardovelli, and then there was a 10-year gap until 2004 when we did the first significant atomization application. So by that time, Gianluigi worked on medical applications, and it's Bianchi from Bologna who took over the strong lead that Gianluigi had in making beautiful visualizations, and he did this visualization here, and together with my PhD student Anthony Lebois-Sautier, who now works at NASA, and of course Rubens Cardovelli, who had developed and maintained and improved the code at that time. And so it was for a Society of Automotive Engineers conference. It was a diesel jet, and you can see how rapidly the topic has then accelerate and how rapidly it has developed. We had 5 million grid points in 2004, then 1,000 more in 2010, then 10 times more, but cheaper in 2016. And then we went to 4 trillion grid points actually a few weeks ago or a few months ago with my PhD students. So we really developed that. Gianluigi was watching this with a lot of interest, but it was not the core of his activity at the time. And it is now, we crossed some hurdles, and now we can really bring some interesting applications. And in fact, there is a medical application to all this, because of course, a lot of diseases are transmitted by small droplets that come out of your body or if your mouth, principally, when you cough, when you talk, when you laugh, when you do a lot of activities that we all do. And these droplets communicate diseases such as the flu. It was known for a long time that someday it will transmit a disease that we could not cure easily. And people had researched that even before COVID. So that will be the more scientific part of my talk. How much time do I have left, please? Half an hour, okay. And it was actually studied even before COVID by people studying the other respiratory diseases like SARS, MERS, and so on. In fact, it's interesting to see that Pasteur thought that the pathogens were transmitted by dust particles. That's why you vacuum clean your houses. It's not because you want them to look neat. It's because the dust contains pathogens. Okay. So paradox is, well, that's the first joke of the talk. Why do we have mandatory masks and no mandatory vacuuming? Gianluigi always told me, Stéphane, you don't say enough jokes. And finally, the first one is on page 14. There was, at the time of the influenza epidemic, there was strong pressure on people to wax the floors and in addition to wear the masks. In 1930, Wells, who studied atomization and diseases a lot, introduced a distinction between droplets and aerosol or droplet nuclei. That was a kind of fateful distinction because the medical doctor misunderstood Wells. They said, okay, if a disease is transmitted by something smaller than 5 micron, this is an aerosol disease and we should all wear masks and stop breathing in front of each other. But if it's the disease is transmitted by aerosols larger than 5 microns, then the droplets will immediately fall to the ground. It doesn't matter if we're in the same room, just we shouldn't spit on each other and everything will be fine. I'm simplifying this enormously. This has resulted in a kind of fight between medical doctors and physicists. The physicists understood that there is no magical barrier at 5 microns, that the droplets of 4.5 microns behave the same way as the droplets of 5.5 microns. But the medical doctors didn't understand that. And it was the WHO announced that COVID is not transmitted by aerosols. On what basis is absolutely not clear. I've reviewed this for some legal issues. There was a bus near Wuhan where people transmitted the disease. They didn't move in the bus, but they transmitted it at 4 meters distance. There was a restaurant. Nevertheless, the WHO said, we talked to the Chinese and the Chinese told us they reviewed 72,000 cases of transmission and none of them was caused by aerosols. I mean, how can you say that? I mean, how can you review 72,000 cases? That didn't make any sense. But the doctors really clung to this. So I'm happy to hear today that Gianluigi had this good connections with medical doctors. He would have been useful here also to enhance the discussions with the medical doctors about these topics. So This is a view of a sneeze performed by Lydia Bouriba. And so you can see in this that there are some kind of balls of droplets that are transmitted. And they are similar to something known in physics as a spherical Hill vortex. And I wrote some equations about this. You know, during the first confinement, you had nothing to do but stay at home. And so it was very good for doing mathematics. And so there are some solutions that you can find to this. The solutions were expanded by my colleague Bala. So this is the first exact solution that I found using a hypergeometric function. But then Balachander had expanded them. So here is the view of the puff of droplets moving forward. And then Bala and his colleagues, together with Soldati, had made a lot of attempts to predict the trajectory of the droplets and the typical timescales for the droplet heating, evaporating, and so on, settling. And so, but one thing we don't know is the initial distribution of droplet sizes. And this is very important because if there are a lot of small droplets, the small droplets go very far, very quickly. And then you are really in a lot of trouble with just one person sneezing or talking in a room. It will create a lot of droplets everywhere in the room. And well, I must say now with the Delta variant, I am persuaded that it's exactly what happens. You know, a lot of droplets go somewhere. You know that the Delta variant is supposed to have an R0 of 6, but if you look at other diseases like measles, measles were claimed to have an R0 of 10 or 12, but in some publications goes up to 60. So you really can have a few droplets that that go very far. So Lydia Bouriba tried to visualize that and did visualize that in great detail using high-speed photograph of sneezes. So you see them here. You see this typical phenomena of droplets with these very thin bridges between the droplets called beads on strings. And we decided to try to simulate that. So we put this red box, simulation red box here. This is the mouth and mole of the mouth. This is the tongue. This is a droplet above the tongue. Well, we didn't do exactly that. But I will tell you later exactly what we did. First of all, there are some experimental results. So that's the droplet size distribution obtained by Dugwid in 1946. It's old data, but it's actually the best data. And so here you see the diameter of the droplet in microns. So there's a peak around 12 microns. Okay, so so this would be the limit of Wells around 5 microns. And this is another set of data from 1967 by Loudon and Roberts. But it's clear reading Loudon and Roberts that they made a lot of manipulations for the droplets below 20 microns. So you can't really trust what is below 20 microns. So it's not clear that this gap is real. Let me go back one slide. Which manipulation did they do? Well, they looked at the droplet impacts, or so-called splats, on a box they used to count the droplets. So it touches another subject that we worked on, the droplet impacts. It's following the movie by Giorgio of the droplet impacts on the layer of water. We studied droplet impacts in all sorts of circumstances with my colleagues, in particular Christophe Jostrand in Paris. And so everything is connected. See, but we had no idea at the time that this was connected to diseases. So I replotted the data of Dugwid and the data of Loudon and Roberts in a logarithmic plot, which allows you to see some trends in the data. And you see that roughly everything is fitted by the Pareto 1/d² fit. The Pareto distribution is the distribution which is like 1/d to some power n. So here the power is 2. And it's amazing. It goes over 3 orders of magnitude almost. And so the question is this real? There are more recent data, but it also can be compared to what people thought. And before I show you the other data, I must say that Wells in particular believed a lot in the log normal distribution. It's a distribution which is loved by mathematicians, by physicists, by fluid mechanicians, which I've written here. It's supposed to describe everything in the universe, maybe even star distribution in the skies, but here it doesn't work. It is this green line, and well, it would work here, but it doesn't work here. Well, here you could put another log normal distribution. The log normal distribution looks like this bump. So physicists have no end of, and mathematicians no end of creativity when they have to explain that they're not wrong, but they are right after all. So they say, okay, no, it's not a log normal, but it's a superposition of several log normals. I don't trust that. I think the only thing you can say here is a Pareto fit. The superposing several log normals is not right. Before I say more about that, these are other more recent data. So again, you see these oscillations. So this look very different from my Pareto distribution. So why is that? The Han, Wang, and Huang, in fact, don't look at the number frequency, but the volume frequency. So they multiply this data by d cubed. So that's the first reason why they look different. The other is that droplets that come out of your mouth are grouped into several categories. They are the droplets that just come from the fluid sitting on your tongue, which are bigger and slower, and those which come from down and from the respiratory tract, which can be smaller. So it is possible that in some cases there is indeed a superposition of several modes, so that could explain this this fitting. Moreover, there are two measures here. So this requires some investigation. Numerical simulation can bring that. So we are going to there will not be a lot of equations in this talk, but we are going to simulate and study these equations. So these are the Navier-Stokes equations, the same way studied with Gianluigi at the time. That didn't change. And an important aspect here is the two formulations for the surface advancements, either the surface velocity or using a characteristic function. The second possibility is the one we use in volume of fluid and also in level set formalisms. So we here are going to use volume of fluid. We are going to use the height function method for curvature and surface tension, and a fixed grid in the so-called Paris simulator code, which was developed with Rubens Cardovelli, which is kind of the grandson of the surfer code that we wrote with Gianluigi, and or the great grandson, because there were two codes in between, developed by Stéphane Poppinet, who was a great student who also developed a lot of the volume of fluid methods in the past 20 years. So here is a typical case that I've already shown a lot, but it's well documented and probably easy to understand. So we can imagine that you have some some fluid sitting on your tongue here, and then the fast gas stream coming from a sneeze. And this will atomize. What you see here are the big droplets being atomized, and then the little blue and red and the little dots here are the vorticity created by the flow. I have some parameters for this flow here. So the density is higher than the real density, but that's for simplicity. We can, I will show later more realistic simulations. We have surface tension, more or less the true surface tension. And the boundary layer height here is 100 microns. So that is pretty small. So here are the dimensionless numbers. So the Reynolds number is important. It measures how intense the flow is. So 8,000 is not enormous, but it's already rather very large. And here is the amount of computer time we used. So and the number of cells. So I mentioned a 4 trillion cell computation. That's an older one, which is smaller. And the total CPU time it cost was 20 million hours. And so here is a view of the simulation. So you see, so that sort of shows you the progress we made since Gianluigi's movie. We can have now have a much more detailed view of what happens, but it's essentially the same thing. We see the interfaces and the droplets forming. We can see here the effect of the resolution. You see this sheet here is not very well resolved. M0 means the smallest computation, and M3 is the finest grid. And you see here, we still see the sheet is sort of has this kind of unphysical features here. And you have to trust me when I say they are unphysical or here. And then when you resolve the grid better, you see this kind of tube here, which is called Taylor-Kulik rim. Eventually it takes this shape, which is probably the correct physical shape. Okay, so this shredding or numerical breakup is unphysical. These are views of the kinetic energy dissipation. And so we are now able to really balance the energy budget to show that the kinetic energy dissipation balances exactly the loss of surface energy and kinetic energy in the flow. But that's a very recent result obtained by my postdoc, Leonardo Circo. And we can match typical correlations for the so-called Dimotakis velocity. And so I apologize for these boxes. This comes from the Mac to PC conversion, but it means that eta is approximately 3 microns, and the Hintze scale is approximately 350 microns. So these are technical details. I have more details about the sheet and rim formation dynamics. So this is something we worried about a long time. How does this sheet forms? Because the thickness of this sheet will eventually control the size of the droplets. So we'll explain the droplet size. Now we know that it's not really the initial size of the sheet that matters, but when a hole will form in it. And that there was very recent experimental work also by the group of Detlef Lohse and Palaf Kant in 20 that has investigated that. At that time, this is work from 2015. At that time, we did discover that holes, which are shown here, form in the sheets, and that the holes are the precursor of these ligaments, or these ligaments, and that this is what controls the droplet size, the formation of holes. That we did discover at the time, although we still wondered about what was the spacing of the sheets. We did also discover the holes. We were not sure that the holes were the main mechanism for droplet sizes. Now we are sure about that. Here is a view of how the ligament breaks into droplets. So this is interesting. You see the second movie by Gianluigi I've shown of the threads breaking. So this is the equivalent of that. but with this multicolored thread. The color here indicates the horizontal velocity. So the thread is very irregular, especially in its velocity at the beginning, which gives a much more realistic view of the droplet formation than in the old movie. But Gianluigi was really the precursor of this. And so now I can show you a whole theory of how droplets form in several stages. The primary instability, the formation of sheets, the formation of holes in the sheets, and the formation of ligaments, and the rupture of ligaments. Okay, so we can also look at the interaction of the droplet of a shock wave, which we did with Florence Marcotte. So that's another view of atomization. It is less important for disease propagation, but it's important for many other applications. So you can see here where the blue arrow is where the sheet breaks. So this is a 2D view. We are trying to redo this now in 3D. And I'm going to skip that and move on to something more related to, again, to the study of respiratory diseases, the so-called cuff machine. So King, Brock, and Lundell in 1965 made this experiment. So you have a pressure chamber here, you have a tranquilizer, so you have a smooth flow, you have a test section with this black fluid looking across section. It's a closed box with a liquid that simulates the human mucus. What they wanted to know was not how you atomize the mucus in a sneeze. What they wanted to know is that what happens when you have a disease and you have too much mucus in your trachea. So you cough to push it up because your cilia, the little hair that are supposed to push it up naturally, are not enough to evacuate all that mucus. So they looked at the coughs as creating waves on this, but they don't look at strong enough flow to atomize. Now there is an experiment by Palafkant, as I said, that has a much stronger flow where you see this atomization. So again, we use the volume of fluid method. Now we don't use the Paris simulator code, but the Basilisk code of Stéphane Papinet. So we have this geometry. So here the thickness of this film is 1 millimeter. It was previously 100 microns, so we can make bigger films. We have the real conditions of air and mucus. And so we are now completely realistic. The Reynolds number is much larger now than before. It's around 30,000. It was previously at 8,000. And we only do a transient. We only do the initial sneezing stage. So it costs only a million hours of computing time approximately. And so it's also more efficient than Paris simulator. So this is a view of the droplets being created by this flow. We don't show the layer and the box. And this is a view of the layer being atomized. Again, the color is the horizontal speed of the droplets. So the red droplets are the fastest. So you see a lot of red droplets here because they have been accelerated by the airflow. And this flow is in green. So these are slow droplets. So these will eventually fall off. So this is sort of your mouth. It will fall off your mouth with big droplets. And this will create a spray that will go very far with small, fast droplets. And we were able to, again, obtain a Pareto distribution. That's, again, a logarithmic plot. But now it's a Pareto distribution with an exponent of 3 instead of 2 in the previous data. And it compares nicely. So these things, L11, L12, L13, are various degrees of refinement of the simulation, like the M0, M1, M2, M3. So L13 means that we have about 1 trillion points in total. If we had a grid which is everywhere the same size. But the secret is we don't need 1 trillion points because with octree grid refinement, we only have points where we need them around the droplets or in the thin layer. And the stars here, the black stars, are the data by Xier et al., who also looked at the distributions of droplets in a sneeze. So we match pretty nicely their Pareto distribution. So that's the end of the talk. Thank you.
Thank you, Stéphane, for your presentation. Wonder if there are questions, comments. Wonder if there are questions or comments in the room. If there are questions online, I would invite the persons who are online to make their question on the chat. I'm aware that Carlo Nardone, which is online, made a comment or better questions. He was wondering whether, and asking you whether you consider the use of GPU in Surfer.
Oh, well, frankly, Surfer was, yes, we did consider that, but not at the time of Gianluigi. It was a few years after 94. For example, one of my collaborators, Sharia Afkami, considered using GPUs. Eventually, GPUs were used in the great-grandson of Surfer in Paris simulator by my colleague Marco Crialesi Esposito, who is now a postdoc in Sweden, and he did a very nice GPU addition to Paris simulator. It helped do this huge simulation that you have seen on a laptop with the use of GPUs. Very impressive.
Are there other questions? Well, if not, I would just ask you some comments on the, well, industrial application of all these wonderful theories. I understand that you have experience on that. I would like to comment.
Yes. So the applications are, well, initially we thought the applications would be combustion, diesel combustion. But as you know, it's very polluting, so we will not apply this too much to that. Another application is the study of how droplets and bubbles form in waves on the ocean. That is very important. But then when you look deeper, the applications everywhere. A lot of flows are made of droplets and bubbles, and especially in engineering, process engineering, and that until now, people thought we couldn't do this numerically. You talk to experiments, say, oh, you will never be able to simulate that. No, but now we're able to simulate that. So now there are huge avenues. I work a lot with the steel industry and many processes of the steel industry where we think we're going to be able to do that. In boiling, to exchange heat in the ITER fusion reactor, we need to exchange thousands of watts per millimeter square. So we need to study boiling at this super high heating rates. So we have a huge range of things we would like to study.
Okay, if I understand correctly, all your codes are available on.
Yes.
And you are an advocate of open science. Can you comment on that?
Good thing. In fact, around 2000, I met this wonderful young student, Stéphane Popinet, and he made me thinking, right. He said, we at the time we thought we would put copyrights to the codes and we would become rich and so on. And then he said, you should distribute your codes freely. And then I went to see Ruben Scardovelli and Gianluigi and told them we need to put a free license on Surfer. This is much better that way. It's much better for lots of reasons. One is that then you don't have to say, okay, Basically, the professor gets rich and the PhD students do the work, which was maybe the way of some groups in the past. Actually, Gianluigi knew a lot of people. Gianluigi had met Spalding, who had developed a lot of codes at Imperial College, and he was okay with the idea. Maybe he was not enthusiastic because at the time he was still looking for industrial support, and industrialists buying the code may have been a sign of support. But he also realized that it was much harder to sell a code in fluid mechanics than in solid mechanics. The market was 10 times smaller, he told me. And another advantage of having free codes is that if you try to sell codes, you're selling something which was developed with the help of the state, because or the help of your company. The company paid salaries for many years to develop something, and then so if you sell it, you sell subsidized goods. So it goes against the rules of competition. Another thing is that the code is just like a mathematical proof. It's a part of the process used to obtain the scientific results. And as a mathematical proof, it should be open. Sometimes when you look at some codes, you see some errors, and you understand why the authors made the errors when you see what they wrote. So this is another reason why the code should be open. It allows the results to be reproducible. You can rerun the same simulations. In fact, if we still had the exact code used by Gianluigi for these movies, we could rerun the code and reobtain the movies, and that would be better. And fortunately, it was not set up that way in 1993, but it could have been done that way.
Thank you. There is a. Okay.
Sorry, just a question. What about applications in no gravity environments, like in space?
There are enormous applications in space, because in space, surface tension dominates. So all these surface tension dominated flows, like the one we have seen with the thin thread breaking, are very important. We even used the nephew of Surfer, because there was a lot of evolution of codes, and one of the codes of Stéphane Poppinet was directly made after Surfer, which nephew of Surfer was used by Emmanuel Horry and Andrea Prosperetti to imagine a pump which would be used with bubbles, which would push fluid in space, which was not easy because the bubbles are not moving naturally as they would on Earth in the tubes in space. It was in fact patented by Horry and Prosperetti.
And now there is Alfio, which is online, is willing to make a question.
Stéphane, thank you very much. Really very great talk. Very inspiring from the scientific viewpoint, and also I really appreciated the connection with the early Gianluigi contributions. I have one question. Is not really a scientific question. You started mentioning the say kind of ambiguous or questionable statements made by WH authorities.
Yes.
And we have all experienced this fuzziness in the communication from WHO. And on the other side, you really made a very remarkable analysis on the fluid dynamics of droplets and aerosols that stem from cough, and so that may have an impact in the understanding, comprehension of the COVID spreading. And I'm wondering if this kind of research or similar kind of research eventually had already or will influence the WHO opinions, or say the information coming from the general public to the general public from the authorities.
That's a very good question. I've in fact talked to journalists even about that, and to legal people and so on. But I've never met WHO researchers or officials. there has been in a number of newspapers an account of this fight between physicists or mechanicians or mathematicians, such as Linda Moore, and medical doctors, why they didn't want to believe the physicists. There has been also anecdotal evidence from Detlef Loze trying to talk to virologists, and virologists telling him, we don't need you. And so I think it will be even worse with the WHO, which is more political and maybe less scientific. So no, we cannot really influence those people. We can do our scientific work. There were mechanicians such as Bill Nazaroff, who are well known in mechanics, who have written papers even before COVID on the propagation. We have to make this work better and better. We have to make models. For example, with some work, we could make a model of if we talk in this room, or if someone sneezes but wears a mask, how rapidly, how many droplets will go where. We can. There's an excellent work by French scientists, including Bruno Andreotti, with a model, a very detailed model, with just one unknown is how much virus there is. It can actually infect you in one sneeze, and then predicting the whole history of potential propagation. We can do that, but influence in politics, to me, that's beyond. But maybe people like Lydia Borouiba, she's a mathematician. She worked on simulations of turbulence, but now she does these things. She talks at hospitals, she talks at medical conventions, so maybe she can do that. But I don't think that we can do anything.
Thank you.
Okay, thank you. There are no other questions. Thank you, Stéphane, for your presentation. And it's now time to end this session. I would like to thank both of the speakers, and let's start with the coffee break. Thank you again.
Okay, so welcome back from the break. Sorry for calling everybody back so loudly, but we're already 15 minutes beyond behind schedule here. So we're going to start with the second session in ZagDay, this event in memory of Gianluigi. The themes of this session are data-intensive computing and scalable data analysis. My name is Luca Pireddu. I'll be chairing the session. So I just want to say, I had the pleasure of working with Gianluigi for about 8 years as a member of his group. I'm very happy to say that he's a really good mentor to me. I was really happy to have worked with him, to have this opportunity. And as we worked together over the years, I had the chance to get to know a bit and appreciate many of his qualities, and even some of his sharp edges, let's say. One of the qualities I admired the most was his uncanny ability to spot very early on those most important game-changing problems in the field of interest. So much before most people even realized that the problem existed, let alone that it was important. So for instance, as biological and biomedical science has started to become data intensive, noticing how people worked, he was very quick to notice that data management, for instance, would become sort of a critical hurdle to having the research process at scale. And he soon realized that the analysis of the mountains of data that would be produced by the up and coming technology would quickly lead to problems that would need to be solved to fully leverage those new technologies and new data acquisition technologies that were coming into play. In the same context, seeing the necessity to have more sophisticated laboratory and data analysis procedures to deal with this data, he immediately understood that keeping track of how data sets and results especially were generated would become increasingly difficult, but increasingly important to ensure the reproducibility of science and the auditability of clinical processes. So on his research journey through these problems, Gianluigi met and got to collaborate with the speakers that are going to be joining us in this session. Each of them will present state-of-the-art work that is in some way derived or at least influenced by the work that was done in collaboration with Gianluigi. So the first of our speakers today is Jason Swedlow, who is joining us remotely. Jason is a professor at the University of Dundee in Scotland. He leads the Open Microscopy Environment Consortium, also known as OME. And he also leads Glencoe software, which commercializes the OME technology. His talk today is titled OME Bioformats, OMERO, and the IDR, Making Bioimage Data Fair on a Global Scale. So Jason, if you're there.
Good morning, Luca. Yes, I'm definitely here. So I will share my screen.
Okay, I'll see the microphone to you then.
Okay, go ahead. So hopefully you're seeing slides now. I would just like to say good morning to everyone. A huge thanks to Luca for the invitation to join you today. A massive apology for not being able to join you physically. I think you all know it's a very tricky time. The kids are back in school here in Scotland and have been for a few weeks. So guess what? Case rates are taking off again. All of the terrible things that we worry about are happening. So it seems safer to be here, to stay here. It breaks my heart not to be able to join you. So a deep apology for that. I'll tell you a few anecdotes about Gianluigi as I go forward. I'd just like to say huge thanks to his family for sharing him with us. Gianluigi and I met in many cities around the world, toured around. I know what a strain that is. My youngest daughter, recently graduated from university, and she recently told me that when she was young, I told her that I was an academic professor and a university professor, she thought I was a secret agent because I was constantly traveling everywhere. So I know that, you know, those types of work that we do in the academic realm can stress families, and just want to thank Gianluigi's family for sharing him with us. So what I'll tell you about today is our work, as Luca introduced, on trying to make bioimage data available in all of the ways that it can be. And as Luca mentioned, we've been doing this work from Dundee. This is a picture of Dundee at midnight in June. It could also be a picture of Dundee at noon in December. It's a lovely town, and I hope you all can come and visit sometime soon. So first, I just try to, and I understand this is a very diverse audience, so I'll try to lay out the problem and then tell you about what we've been doing and intersperse that with work that Gianluigi contributed to that was incredibly important for us. So imaging has become in the biomedical sciences absolutely ubiquitous. Imaging is used everywhere. The reason for that is that while it's great to be an imaging person, my whole career has been based in imaging. You get to make pretty pictures and pretty slideshows and show lots of movies, etc. That's nice. But in a deeply serious way, every one of the images that you see here is actually a quantitative measurement of a biological or a biomedical system. And so the pixel values are in various ways related to constitution of a biological system, a cell, a tissue. Those pixel values can report on molecular interactions. There's an enormous amount of capability that has been developed over the last 2 to 3 decades to use imaging as a quantitative measure. You see this throughout the world of bioimaging, throughout the world of biological sciences, the life sciences, the biomedical sciences, etc. And so I just want to start a timer here. So this all started happening way back in the mid 80s. Imaging started to become used and really exploded in the 90s and early 2000s. And what has happened over the last about a decade and a half is the realization that while these data are certainly measurements and are can lead to quite profound insights, those data as measurements start to become a resource. And so I mean that in the most general way. For example, an institution might collect a large amount of data to be able to represent the systems or the individuals it works on. A large global multinational project might collect many different data sets and want to bring them together. Or even we might think about actually publishing data, this type of data routinely and doing calculations and reanalysis on it. And this problem is what we've been working on in the OME project since about 2000, since we founded the project. What I want to tell you today is a bit of an update on what we've been doing, where we're going, and also how Gianluigi contributed to that. And so in about 2000, we realized that while there was lots going on in the imaging world, so lots of people were developing new imaging capabilities, new imaging technologies. There was a huge amount of work on new analytic and processing tools, various advanced visualization, but connecting all of these different functionalities wasn't a solved problem and was becoming a barrier. And that's the problem we started working on. That's where project I'm going to tell you about, OME, has really been focusing its efforts for the last now almost 20 years. I should emphasize everything you're going to see is open source. It's completely available and ready for reuse. And I think that's one of the things that has been great about working with colleagues like Gianluigi and his group, to be able to present something to the community and have people take it and bend it and change it and use it in all of the ways that they can. And that's really been an awful lot of fun. The website is on the bottom of the slide should you want to follow up on any of this. So I'll spend a little bit of time talking about the technology. This is all open source software that is freely available. As Luca mentioned, there's a commercial company, Glencoe Software, that commercializes this as well, but everything is freely available for the community. So what you see on the slide now are a series of words. These are names of software tools, products, data specifications, et cetera, that we publish for to the world and are used now around the world for all sorts of different types of applications. Indeed, in the biomedical sciences, the life sciences, but also in marine biology and actual material sciences now. So these tools are used in a lot of places far beyond anything we originally intended. And so I'll just tell you about a few of these. All of these words are names you can look up on Google or your favorite search engine, whichever you use, and you can get more information there. So one of the great success stories of OME is a library called Bioformats. We realized very early on that there was a problem in the imaging community is there are hundreds of different proprietary file formats. And that's just a consequence of the fact that there's many different commercial companies and many different developers developing lots of different imaging technologies. And this has just been growing now for the last couple decades. And so on the left side, you have many, many different file formats. And on the right side, you have lots and lots and lots of different analytic tools, and something needed to connect them together. And so we started back in about 2002, working with colleagues at the University of Wisconsin at Madison on a project called Bioformats, which is a file format translator. So from the standpoint of the computational sciences, this is one of the most tedious and boring projects that you could imagine. All Bioformats does is translate metadata and binary data that are stored in proprietary file formats into a common model that other tools can read. As it turns out, this has been a great success story. This is used around the world. It's started hundreds of thousands of times a day. It's incorporated in lots of different open source and commercial software. And what it has done is, as we have been building the various readers for the different file formats that we've seen, it's actually meant that our team has a great amount of knowledge about how data is constructed. And that knowledge turns out to be important for what I'm going to tell you about later in the talk. So bioformats, you can think of bioformats as an interface between various analytic tools and all the different data types that are out there. One thing I should emphasize is that we built bioformats on the back of submissions from the community. So for the last couple of decades, people have been sending us example data sets. So we actually have a pretty large collection of data that we can use to build bioformats, but also test it. And that turns out to be a large computational problem about how you run those types of tests at scale. If anybody's interested, we can talk about that. And the other tool that we've been working on now for several years is called OMERO. OMERO to a computational scientist looks pretty familiar. So it's a typical sort of 3-layer model, various data sources on the back end, a middleware application that we call the OMERO server, and then connecting through an API to a variety of different clients. There's lots of sort of technology in here. All of this is published and again, open source. So I won't spend too much time going over this, although I will tell you a couple things about this. One key point is that this API that provides a secure connection to via standard internet is cross-platform. So we can work, scientists can work in whatever environment that they like to work in. So in the web, Java, C++, Python, etc. And we have various ways of handling all of the different types of data that one has to handle in the imaging world. Now, one very special concept in OMERO, and this comes out of work by Josh Moore, who I think is attending this session. So Josh really is the sort of father of OMERO. Josh built a lot of the original concepts of OMERO starting back in 2005. Josh realized that what we needed to do was build a data management system that was flexible. And so we had at that time a specification, was written in XML, our so-called OME XML schema for the various metadata types that we had to handle in imaging. And what Josh did is build all of the code generation tools so that the API, the database, et cetera, were code generated. So we're not written by hand, but we're actually written by the OMERO system. Now, what that meant is we could build OMERO based on the imaging metadata that we knew about. But in principle, it meant also that someone could come in and update this model and build a data system that handled different data types. Now, I emphasize in principle because that's a significant amount of work, and that's something that we didn't have time to do. But at one of our users meeting, this interesting gentleman comes up to me. He says, "Hello, my name is Gianluigi. OMERO works for images, but it could work for other things as well." And I said, I had met Gianluigi before, and I said, "Yes, we think that's true, but we've never done that." He said, "Well, I have." And Gianluigi had actually taken all of the OMERO models and with his colleagues, Luca, and Simone, had turned OMERO into a metadata management system for SNP imputing in genomics. And so for the workflow systems that Luca just mentioned, there was a critical problem around identifying the layout of a imputing calculation on a large cluster. And so this is a figure from a paper we published with Gianluigi, where effectively this interface between red and blue is looking at the complexity of a family that's tracked, whose SNP variants are tracked, and basically the computational time here on the vertical axis versus the number of cluster nodes. And you can see that there's effectively, there's a region where an optimum is reached, and there's no further acceleration in the calculation is achieved by adding more cluster nodes. And this is a key point when you have shared computational resources, et cetera. I think this was really interesting. So as Luca mentioned, Gianluigi saw a way to take a technology that was coming out of a completely different area, but it had concepts he could use, and more or less bent them to his will. It was really exciting to see this, and was the beginning of many years of a great collaboration, which I'll talk about more as we go on. So when we build systems now, this is sort of the layout that we end up working with, and this sort of reflects the standard way that imaging works in life sciences laboratories, in R&D facilities, both in academia, biotech, and pharma. So there will be many different imaging modalities, generating reasonable amounts of data per day into the terabytes per day. Those are written down into large file stores, almost always in these native file formats, these divergent file formats that are many different versions of which we know of. So bioformats is sort of the common unifying interface that provides a way that anything can look at that diversity of data types across many different modalities. And so so that's the first thing that we do to make it possible to access these data. And then we put OMERO on top of bioformats, and what that does is provide another interface, for example, out to a remote client, a web-based visualization tool, or perhaps to analytics running on large clusters. And so this is what you're seeing in this diagram is this idea of common interfaces providing access to this diversity and scale of data that is now common in the imaging world. So just a few examples. So this is a screenshot. Maybe I'll just go back. I apologize. What you're going to see here are screenshots up on the top right here of clients. So this is a web browser client that's running, for example, on my laptop. But you have to imagine that the screenshot is showing you everything that's sitting underneath that. So this is one. This is a certain. This is so-called high content screening. This is used in drug discovery a lot. Obviously have some file organization, we have images, we have analytic metadata in this case. And so in this next slide, you see a very different imaging type. This, for those of you in the digital pathology world, this is in the oncology world, this is the TCGA data set from the National Cancer Institute in the United States. So again, a completely different type of imaging data. So this, in some sense, this is bioformats at work, being able to point this application at many different data types. Have many different types of metadata here. This is metadata coming out of the TCGA resource. So for those of you who are familiar with this, you'll know what this is, but those of you who aren't in the world of pathology, so this is various analytics that are counting nuclei, the various different types of cells in these cancer tissues. And this, hopefully this is familiar. This is obviously an MRI of a human head. And again, this is bioformats picking up different metadata and different binary data and making all of those accessible. Those of you who have some knowledge of this will recognize some of the DICOM tags up here in the metadata panel. So this gives you an example of the kinds of things that we can do. We can bolt on lots of different software, lots of different open source or commercial software to OMERO through these interfaces. And all of these are examples of things that have been done by us or by others. And so all of this is published and available. We published a whole series of guides on how to do this. And so these are used and now they're used by a wide variety of people for training tools. So that's been a real success story. I won't say too much around the more about the analysis, but what I want to shift now and focus on for most of the rest of the talk is about using OMERO to share and publish data, because that was something that people were talking about, but wasn't clear how to do that with these types of data that are these very large, complex, multidimensional images. So just some examples. This is at Oregon Health Sciences University in Portland in the United States. This is Joe Gray's group. They're doing they're looking at how breast cancer cells respond to drugs in different microenvironments, so different extracellular matrix formulations. All their data is managed and published with OMERO. Back in Europe, this is in the United Kingdom. This is the PDBE, so the European Protein Data Bank, and they've been publishing EM data. And you can see that, completely different representation, sort of client representation, but the back end is OMERO. In Japan, our colleagues at RIKEN, led by Shuichi Onami, are using OMERO to publish data sets on their system science and biological dynamics database. Again, a different client view, but the back end is the same. Here in Dundee, more or less a kind of a side project. We built a data publication, a data sharing system for a colleague here who was teaching anatomy. He had several students who wanted to be able to visualize the slides he had for in a teaching environment. He had several slides that were fairly precious, and sharing them with students was a little bit risky, and so he wanted electronic tools, so we built that. As you can imagine, when COVID came along and shut down in-person teaching, this became incredibly valuable, so this has been important. And in fact, Gianluigi himself, Luca Leonis and colleagues, built a teaching system that integrated into Moodle, which is a popular educational environment. And so the same idea, taking these data and taking digital pathology data, whole slide imaging data, and making that visualizable in a web-based environment. So, you know, again, this is an example of seeing an opportunity and connecting into tools that we had, but also tools that others had, and bringing them together. Glencoe Software, our commercialization arm, has taken this and built a proprietary tool for visualizing tissue data. And this is from Peter Sorger's lab. This is cyclic immunofluorescence. So this is now taking another view of digital pathology, now looking at the molecular environment of cells and tissues. This turns out to be breast cancer. And this yellow signal is cytokeratin. So this is a very aggressive breast cancer. The pathologists at Harvard Med School have really cottoned onto this because this has been very powerful to see both the tissue and the molecular signals. Glencoe has built a public atlases. In this case, this is human pancreas that has a resource that has been built with Marcela Brasova and Al Powers at Vanderbilt in the United States. So all of these are the same sort of engine sitting underneath, OMERO and bioformats handling data, but then connecting in various different ways to representations in the front end. And so what that's meant is that we've made a lot of progress towards this goal that's maybe some of you have heard about, this idea of making data fair, so FAIR, or findable, accessible, interoperable, and reusable. And so these are sort of high-level words, and if you go back to the original paper that sort of talked about these ideas from Wilkinson and colleagues, you know, these are the technical capabilities that we are implementing in OMERO, and we think we've seen now several examples where this has been valuable both for institutions and just managing their own data, but also for publishing data globally. And it's really that last idea that I kind of want to move on to now is taking these data sets and making them a fully public global resource. And the story is about a resource that we've been building called the Image Data Resource, or IDR. And so IDR starts off as an idea, which is, publishing data in genomics, for example, and structural biology is now very well established in the life sciences. But publishing imaging data, at least back in 2014 or 15, when we started this, was felt to be not possible, or at least too hard. And so we wanted, because we thought, well, that, if something's too hard, it sounds like a good challenge. So what we wanted to do was to start thinking about all of the different types of imaging data sets, see here on the left, and integrating them into a public resource, making, annotating them, connecting the analytic results that were coming from people that were publishing data, making those available, for example, in a web browser. Given the data volumes, we would have to think about cloud-based analysis, but also making those data downloadable as well. And so this has been an interesting journey over the last several years. This is now running at the European Bioinformatics Institute in Cambridge here in the UK. The URL is there. And this is now what started out as a vision in 2015, came into reality in sort of the middle of 2016, and now it's running in production. So just to give you an idea, this is the scale of what's being published currently, closing in on 300 terabytes of data, several million, tens of millions of files, several million multidimensional images, and probably most importantly, a large number of annotations of different information about the images that are attached to the images. IDR is heavily used. These are IP addresses we can resolve in a year. And so it's used by people all over the world. And what we're doing is publishing data sets associated with papers that are published in journals. And so this idea that a paper now is published alongside the imaging data that is that supports the observations in the paper, And that's that is the goal of the IDR, and we're now doing that routinely. These are some of the journals that we are cross-publishing in. IDR is recommended by the Nature journals and several others as well. One very important point is that IDR focuses on what turns out to be a small number of images. And so we're really looking for images across the various domains that I started out with, but where we have a substantial amount of associated information, metadata. So for example, the genes or maybe the chemical compounds, biological information like cell lines or strains, antibodies, other metadata that makes the imaging data as rich as possible. Wherever possible, we want to connect that metadata and the imaging data with phenotypic, so analytics or maybe phenotypes that have been called by the authors, any ground truth data. So we're really looking for very rich data sets, and this turned out to be a small percentage of the total of all of the different imaging data that are collected and published that are used for publishing papers. So it's a very important point that we're looking for what we call reference images. So this is a small percentage of the total imaging data that's published, but nonetheless a reasonable number of studies. And this idea came out of collaborations between the European infrastructures of Eurobiomaging Elixir, and I'll talk about that more if anybody's interested. Now, what that means is that we are focusing on a small subset of the data that are published. So in a so-called added value or knowledge base, there's different words for this, but we're really trying to use a lot of curation and interaction with the authors to build these reference data sets and make them public. Of course, that's a small percentage of the data that should be published, and that raises the question, what about everything else? And so our colleagues at EBI, at the European Bioinformatics Institute, have started building the BioImage archive, which effectively is a repository for the rest of the data. And that's a project that we're closely involved in, we have a lot of interaction with. And you can imagine that these two types of resources sort of depend on each other. The archive needs a minimal metadata specification that has now been developed, but it also to sort of to help feed data reuse, it needs highly annotated metadata, and that's where the IDR comes in. And so we actually have a really nice interaction with them. Now, I want to emphasize that what I'm telling you about is activity currently ongoing in Europe. Our colleagues in Japan, led by Shuichi at Riken, are building something similar for Japanese researchers, the SSBD database and the SSBD repository. Similar activities are now kicking off in the United States as well. And so this really is becoming a global capability and a global resource. One of the things that's really great is to see that, again, these are all based on, they're reusing a lot of the OME's technologies, bioformats, various file formats, et cetera. So it's really been a very fun and exciting development over the last several years. It's fair to say that in 2021, imaging data is becoming routine. Publishing imaging data is becoming routine. Back in 2015, it wasn't possible. So we've made a lot of progress over the last 5 or 6 years. We're very grateful for that. So quick tour, lots of different imaging data, some of which you'll recognize. I won't go into the details of these, but lots of different data types, again, with all of the different metadata and so on. We even have what we call a geographic screen. This was from the Tara Ocean study, where the Tara schooner sailed around the world, dropping buckets into the ocean in various locations, doing a metagenomic analysis of plankton. And so obviously the metagenomic data is published in various online resources, and we have the imaging data linked to that. Quick tour, we have data like large tissue images around the fate maps, for example, of mouse embryo. We have machine learning data sets. This is from Anant Madabushi's lab. This is a deep learning study looking at cardiac biopsies. Some of you might know the project called the Human Protein Atlas. We have the tissue data from that, which is localizing and several thousand antibodies in human tissues and in both normal and diseased tissues. We have all of that, and we have all of the associated metadata. Just a quick SARS-CoV-2 story. Hans Klaver's lab back in May 2020 were publishing a paper showing the first infection of a SARS-CoV-2 virus of human intestine. There was a lot of discussion about what tissues the virus infects. This was published in Science. There's electron microscopy, very large EM maps that were published and that were also available. We published those in a nice visualization environment so you could see them. And then the raw data was also published by our colleagues at EBI. We annotate the imaging data with many different ontologies. These are just some of them. This actually turns out to be a huge amount of work. Just one example. So this is the annotations associated with one of the images in the IDR. So you can see a compound name, but many different types of compound IDs. We're trying to capture as much information, as much metadata as possible. So we have PubChem IDs. There are different IDs that are used in this field. So we're trying to capture them all. What that means is that we can actually start, and this is just a one example, we can start to do searches. And so this is searching the IDR for remdesivir, a compound that's used for, that has at least had some success in interfering with SARS-CoV-2 infection. Sure enough, colleagues from the Fraunhofer Institute have published a paper, and we published the data showing a dose response curve now here for the infection. This is a high content screen. What you're seeing here are human cells where they are at high concentration. You see lots of cells, and at low concentration of the inhibitor, you see a lot of cell death. So you lose cells. And so this was basically a public demonstration that remdesivir at least can protect human cells. You're probably wondering about whether hydroxychloroquine has any effect, and indeed it doesn't. And so that's all public data. So we've built the IDR. We now have sort of two IDRs running side by side, a cell-focused IDR and a tissue-focused IDR, and these are all publicly available. We've started making the data analyzable. This is an ongoing project, but we're trying to make it possible for people to run Jupyter notebooks, for example, against IDR data in various ways. This is definitely a work in progress, but it does seem it is working, and it allows us to incorporate analytics from that analytic workflows alongside data from published papers, and so that's very exciting. And finally, for those of you who are very technically oriented, we've been making it possible for people to reuse IDR and basically take everything that we've been doing in terms of the deployment on an OpenStack cloud and make this deployable. So I know this is an extremely technical slide. Those of you who understand about building large systems will recognize some of the terms. The URL is there. The key point is that we are working now. What that's done is allow several different IDRs to start to appear. There's a marine biology IDR. There's several others, and we think that this is very exciting. And the idea is that hopefully these all start interacting with a central archive. And that's kind of a 5-year vision, but I think that's probably the way this all has to go. So just to summarize what I've told you, we've been building these public resources. They really are available. We're doing all of the curation, so the metadata is linked, working on reanalysis, and that anybody else can reuse. Again, as I mentioned, everything's open source, and I'm happy to pass these URLs to anyone who's interested. Just get in touch. So where is all this going? So really what we've been looking at over the last couple of years is our strategy around file formats. And I mentioned bioformats in this translation system that has been so successful. One very important aspect of this is real-time translation. So we're using the native files and in real time, sort of on the fly, translating metadata. Some of you might immediately start thinking about, wow, how does that scale? And the answer is ultimately not terrifically well. And so one of the problems is that we have many, many different vendors making lots of different file formats, and these things are getting larger and more complex, and it's just getting bigger and bigger and bigger. But one of the things that we saw as we looked over time is the number of new file formats, and you sort of see this on the right side of the slide, is starting to tail off. And so we publicly more or less said, we're not going to, this doesn't make sense anymore, coming up with new file formats every time a company comes up with a new imaging system. We have to be smarter. And we've been putting a lot of work in trying to be smarter. And so the summary of a lot of work by Josh Moore and several others is that we've been trying to come up with a new file format, so-called NGFF, or next generation file format. Excuse me. They're testing the fire alarms in my, okay. They're testing the fire alarms in my office today. So hopefully that wasn't too terrible. The key point is that we are working with the community. All of this is open source, and you see the URLs there. Everything's on GitHub for making these file formats to be able to scale and to work on the in cloud-based object stores. I'm skipping over a lot of technology, but everything's published. We've actually made substantial progress here. We have multi-scale image data representations. We can represent all the labels that are important in machine learning. We have representations for high content screening, and we're working on others. For those of you who are interested, I'll suggest you to have a look at this URL, ngff.openmicroscopy.org, and more is coming. And what we think that this enables is a different way of thinking about handling these data. So I mentioned bioformats and this on-the-fly translation. This is the way everyone that we've been working, and a lot of people in this community have been working now for, well, the best part of a couple decades. We think now it's time to start thinking about a one-time conversion into an optimized format that could be stored locally, but also could be stored in the cloud. And these formats that we're using, the so-called ZAR formats, are cloud competent. They can run an S3, which is an affordable storage mechanism. They also allow streaming, so a completely different way of working with these data. As opposed to having very large collections of data on a disk, we can now start to stream this data. And a metaphor is to start thinking about the Netflix of these types of data. That's obviously a ambitious idea. But we think that this type of data access will transform how people can work with these very large data sets, which we're all using. One of the key points now is that rather than forcing people to download very, very large data, terabyte collections, we can now use that streaming to have interactive access, and that all works. I should say again, like all of our work, this is being done with the community. And so we started this with a discussion on the ImageSC forum. This is where a lot of this work is discussed. We have a preprint in bioRxiv. Should you want to look on this, just Google OME NGFF, you'll find it. Paper hopefully will be published soon. And so where we're going, hopefully, is that many of these different, this sort of panoply of different file formats converge on a single representation. We hope that happens. It's not something that's going to happen in the next few months, but hopefully in the next few years we get there. So just to summarize, I hope I haven't gone on too long. We have several different tools that we published, all open source and all available. We've had, I think, some success in working with the community and making these a really valuable tool, especially with the image data resource. We've shown that fair bioimaging is possible, and we think we're showing that it's scientifically valuable. And probably most important, what we're seeing is a global community of open source projects, imaging networks, and imaging infrastructures all coming together. I want to thank everybody who's been involved in this work, in particular, a lot of the funders in the UK, Europe, and the United States, very talented team. And in particular, several different collaborating labs, including Gianluigi's lab, who's been very much fun to work with. I just thought I would just finish with something that I was thinking about, the wonder of working with Gianluigi. And so this is an email thread, and you can sort of see the dates here on the right side. This is back in 2015. One afternoon, I got an email from Gianluigi saying, does your network of informed people, and he's asking, have a copy of the latest version of the work program for health, demographic change, and well-being that will be released in October 2015. So the scientists in the audience will understand what Gianluigi's asking. So the new EU framework is coming out at this time, and he's asking me, do I have any of the draft versions that he can look at? Everyone knows in this community that those are quite prized possessions. And so I wrote back and said, yep, just received a draft, but with strict thou shall be shot instructions not to forward outside of Dundee. Nonetheless, I'm happy to talk to him about it. And I said, I can cut and paste. So I'm bending the rules here, but I hope that's okay. Gianluigi writes back and he says, well, here's the version I have. I just got it from another source. Let's scan, we can both scan and we can compare. And then PS, do they do the shooting in the main plaza for all to see, or is it nobody has seen him since then for a kind of thing? And this is what I loved about Gianluigi, his playfulness, his imagination, his willingness to just kind of bounce ideas around. It was always a joy talking with them. I tried to keep up with this. I responded saying, sure, we can do comparative scans. And I mentioned, obviously I'm in the UK, so everything here is more British and the subtle, but of course we're in Scotland, so there has to be a good war whoop. And I just want to just share the number of times I got text messages in the middle of the night saying, hey, how's it going? Are you thinking about XYZ? I think this is important. And how much fun it was to just share all of those moments with him and just to be stimulated and driven by someone who was so imaginative and just really an awful lot of fun to work with. And I just, again, thank you to colleagues at the Institute and his family for sharing with us. He was just fabulous. And let's just stop there. And thank you so much for this opportunity to share a few memories with you. Happy to take any questions.
Can you hear me now?
Gotcha. Yeah,
okay.
gotcha there. Yeah.
Okay. Thank you, Jason. That was great, especially the last part. And I can attest, I've seen these two, Gianluigi and Jason, at a conference a few years ago, and they just wouldn't stop laughing. They were always sitting together and chatting away. Before I open the floor to questions, if there are any questions from our people who are following remotely, remember you can write them in the comments on YouTube and we'll have them read afterwards. Also, during the presentation, there was an audio return. There might be somebody in the audience who has the YouTube feed open and maybe something's happening there, like we're getting a return echo. Okay, so any questions? All right. I wanted to ask something, or a comment rather. Seeing all the effort that goes into projects like bioformats, trying to chase after the vendors basically with every evolution that they introduce. Do you think there's good probability that you might be able to get the vendors on board with an open format like the one you're creating now to try to put an end to this jungle?
It's a really interesting question, Luca. I will say the short answer to your question is cautiously yes. I don't think it will happen immediately, but I think I could tell you lots of different anecdotes, and I wish I could share them with you over coffee or a glass of something enjoyable. Maybe we can do that sometime soon. I think one of the things that we've been seeing in the across the imaging community, and by that I mean in the scientific community, but also in the technology development community and also in the commercial community, is a realization that we need formats that enable science to be done. And one of the things that we're starting to see is that at the scale that people are now working in the types of calculations and in the HPC calculations that people are doing in AI, et cetera, we're seeing actually the file format be a bottleneck. We OME, in our work on IDR, we see the file format being a bottleneck. That translation that we have to do is starting to become a bottleneck. And I think most people can agree that if the file format is a bottleneck to scientific discovery, that's not very smart, and we have to do better. And so I think for several years we fought. It's been a challenge to get the to get the breadth of the community on board with this. But we've made a lot of progress, in particular over the last couple of years with the NGFF work and a lot of the conferences where we're discussing this. That Josh Moore and others are organizing. We're having representation from the commercial vendors, so they're paying attention. And so I think they're very clear about what they need. And one of the most important things is that we will need to do is respect the requirements of this broad community, and that different members of the community have different requirements. But at the very least, we're all listening to each other and talking to each other. So that may be over optimistic, but I think so. It will take some more time though. It's not going to happen in 2021 or 2022, but we'll slowly get there.
Okay. Thank you, Jason. Okay.
All right.
So let's thank the speaker again then.
All right. Thank you all.
So we'll move on to our second speaker in the session, our dear Petr Holub. Petr is an associate professor at the Masaryk University in the Czech Republic, and he also leads the Common Service IT at the European Research Infrastructure for Biobanking and Biomolecular Resources, also known as BBMRI ERIC. He also co-founded Comprimato Systems, a company that commercializes research results in data compression, accelerated data compression. So his talk today is titled Provenance Information in Medical Research, a quest for dealing with reproducibility issues. Petr, welcome. The floor is yours.
So good afternoon, everybody. Thanks for inviting me. It's really an honor to speak on behalf of BBMRI ERIC, the European Research Infrastructure on Biobanking and Biomolecular Resources, in a commemorative event for Gianluigi. And Gianluigi was a dear contributor of BBMRI ERIC since its practical inception in 2014-15. We met early on, and we met several times a year physically on different events, and we were in constant touch. And Gianluigi was acting as a bridge among different communities, and within BBMRI, he was basically taking care of the translations between the IT communities and the bio communities. And he was acting and sharing those different anecdotes we have seen. He was acting as an incredible bridge sometimes because as he was also fluent and kind of mentally native in both English and Italian, it resulted sometimes in really funny stories, like when I was doing an audit of Italian rare disease biobanks with him. And I was so glad that he agreed on doing it together with me. We were auditing the IT systems of those, because some of the people here in the northern region, they didn't speak English. They only spoke Italian. And Gianluigi was not only doing the review, but he was also acting as a translator sometimes. And I remember once, I mean, it was going with pretty fast staccato, and out of a sudden, I realized he's talking to me in Italian and talking to them in English. Classical computer one-off error, like we know from 4 cycles. So he was, but he was of course professionally the one of incredible people we had, and one of very exceptional people we had in our communities. It's real honor to speak here on an event like this, and I'll share a little bit more as I speak in my presentation. So what BBMRI ERIC is about? It's a federated European research infrastructure, meaning we're spanning more than 20 member states at the moment, plus IARC, which is International Agency on Cancer Research. And we're operating an infrastructure, federated infrastructure, which means the biobanks that are contributing, the biomolecular resources that are contributing to the infrastructure, that are providing services as a part of the infrastructure, have their independence. And we have a number of other contributors, and CRS4 is actually one of those contributors, because as far as I know, CRS4 is not operating your own biobank, but you're operating compute facilities and storage facilities, and you have computer science and say translational expertise on board that bridges different domains. So this is also what became part of BBMRI. Eric and Gianluigi was a core person to establish those links. And as the research infrastructure, we're working on facilitating access to the health and medical data and to the biological samples, and trying to make the data more fair. And we have, and Gianluigi was contributing to that paper, actually, we were even extending the FAIR principles that Jason was mentioning on the previous presentation, findable, accessible, interoperable, and reusable, to what we started to call fair health principles, with the focus on privacy, reproducibility, and incentive aspects. And in this talk today, I'll be talking about those reproducibility aspects. And why? Well, why provenance? Provenance is basically machine-readable documentation of history of objects, be it digital objects or physical objects. And why would we need it? Well, because the last more than a decade and a half is plagued by reports of irreproducibility in high-profile research journals, Nature and others, complaining about it. High-profile international pharmaceutical companies and other companies are trying to reproduce the research results that were published in top-tier journals, and they're repeatedly failing to do so. Because there are things missing in the journals. They are not described. You don't have the complete chain of what has happened to the patients, to the biological material that was retrieved from them, and the data that was collected, how the data was processed. This chain of events is broken in many places, and there are missing bits that are often, of course not always, but often making reproducibility impossible, basically. And if you look at the meta study that was published about 4 years ago by Friedman, this was a meta study already collecting the evidence from other different papers looking into specific aspects of reproducibility. And the conclusion was that between 50 and 90% of medical research is not reproducible, which is incredible. And deeper dig into this looks where this comes from. And again, making a quick bridge between the previous presentation and the current presentation, when we discussed with the optical microscopy communities, what are the sources of irreproducibility? Well, it's rarely the microscope itself. I mean, it can also happen. I'll be talking a little later about digital pathology as well, and the provenance of digital pathology. So there we're using microscopes that are collecting tens of gigapixels large imaging, and you can have reproducibility problems there as well. For instance, we see problems sometimes that different blocks of images are incorrectly aligned. But these are minor things, relatively minor things, and they can be caught by the quality checks. But there are many more problems that are in the pipeline that led to scanning the biological material. So how the material was collected, how it was processed, how it was eventually stained before it got to the scanning device. And then in the latter part, how it got integrated into the data set and how that was used for further research and what methods were used. And again, we discussed today already a couple of times the AI, and the reproducibility of AI was touched upon a little bit. And from our own experience, running a neural network training based on TensorFlow, which is one of the major platforms at the moment that is used for neural network development, it's not reproducible itself. Unless you take very specific precautions, which are developed in the last year or two, because there are pseudo-random things that are coming into the play, and you run the same training twice and you don't get numerically identical results typically. So these are things that are all contributing to this lack of reproducibility. And you can see the distribution of that irreproducibility here on the slide decomposed into the biological material, study design, data analysis and reporting, and then the lab protocols. All of this was one aspect where you still assume that people are behaving, that people are in the research are doing it as bona fide researchers, and they want to follow good research practice, good laboratory practice, and the missing bits and pieces are usually not because of malevolent behavior, but rather because of some negligence or by lack of documentation of things. But there are even worse cases, and talking about the COVID-19 last year, this was an incredible case by Surgisphere, where they published papers on pretty obviously fake data that couldn't have existed, because that would mean they would gotten access to basically all the African population that was infected by SARS-CoV and got perfect data out of it. So we also need mechanisms that are able to support trust in the data we're working with, that are able to document the data in a non-repudiable way. So all of these hydroxychloroquine studies later turned out to be forged on different levels. So these are things that we would like to somehow capture. And as I already stated in the introduction, we basically need to capture the whole chain of provenance, from the source, from the patient, from the biological environment, or even from the environment around the biological entity, to the data generated, to the data processed. And it has to be machine readable. I mean, within the current world, within the amounts of the data we're dealing with, it's impossible to assume that the data and the provenance can be generated manually or processed manually. I mean, Giorgio has mentioned the amounts of data they have in IDR, something like 200 terabytes. One of our data partners in BioImage, Medical University Graz, has recently generated close to 1.2 petabyte of data only for colorectal cancer, for digital pathology imaging, as a part of collaboration with Google on the digital pathology research. So nobody can generate detailed enough provenance information manually about such volumes of data. And we can generate now petabytes of digital pathology imaging within a year, basically. So the amounts of data we need to document is turning really incredibly huge. So the ideal vision is that all the lab automation devices, all the scanners, as well as compute workflow toolings like Galaxy, they need to have inbuilt mechanisms that you can use to generate the provenance automatically, and then you can analyze it in a machine action. I mean, if the provenance is machine actionable, if it's structured, it's in well-documented formats. And OMERO is one of the communities that is very active in development of those as well. You should be able to analyze those things, the documentation of the history, in a machine readable way, or in an automated way. And if you have any requirements when you're reusing data, these quality requirements, which basically means fitness for purpose requirements, should be also expressible as constraints or conditions on provenance. So this is the overall big picture, how things typically look in the biological, biomedical research that is interfacing computer science research. And the documentation should form such a complete tree, linking backwards to the precursors of the data that was processed, that was generated, and to the biological material. Well, we met with Gianluigi, I think it was in 2016 approximately, at some event, and we were both looking at the current situation, and we were pretty frustrated, to be honest. Because of course there was a lot of theoretical work done on provenance in the last 15 years. There was an World Wide Web standard called the W3C Prov, published in 2013, but still the situation about the provenance was not practically changing that much. It was just not available. Well, because it hasn't become part of the tools, part of the systems that we're daily using in research. If it's not automated, nobody will do it manually. We're not paid as researchers to spend our time in basically administrative work. So we were pondering why is this happening and how can we help it? And we also got together with Jörg Geiger from University of Würzburg and University Hospital Würzburg, and started to put together those components that we see as the biggest challenges we will need to handle. The standards were out there, but the problem is that they were also constructed very generic, and they were missing kind of explicit support for many things you practically need for constructing such big chains. So handling multi-institutional provenance or the provenance that goes across multiple institutions. I mean, it's relatively easy if you think about it within one lab. You can take the Prov model of W3C and you can somehow use it, apply it for your own problem and store the provenance locally. That works. But what if you need to link it across multiple institutions and you have to do it in a non-repudiable way? That means that somebody else can't deny that they have done what they have done. And you need to do it in a way that you're processing also personal information. Eventually, the provenance leads to a patient. So you can't put all the provenance in public, because that would mean basically linking it, in case of my own data, my own medical records, that would lead to my medical identity, which is in the Czech Republic, we're using something called birth numbers, like civic numbers that are uniquely identifying all the citizens of the Czech Republic. And this is highly protected personal data, of course. This is not something that you can put in the research domain as unrestricted access data. Another aspect is the provenance has to find a sweet spot between simplicity and perfection of what you want to collect as a part of the provenance. Because if you go too detailed, if the requirements are too heavy, it will be too costly to implement it in practice. If it's going to be too lightweight, it will not capture the information you need further on. Plus, there are many domain-specific standards that are out there, but for many domains, it's still missing. So OME community is developing this since already a couple of years. So Katarina Strambia from Medical School of University of Michigan is developing the optical microscopy provenance since a couple of years already. But not all the domains are as advanced as this. If you look into the provenance of the biological material before it enters the scanning, well, there isn't much available out there, or there wasn't much, and we're still working on actually enabling it. So we were brainstorming since about 2016, and what we realized is we will need a standardization of the provenance on several levels, and it has become a little bit of conundrum that we're still trying to resolve, because we need ideally something that is some standardization environment which is industry accepted. So when you have microscopes where you have NGS machines, the provenance should be automatically spit out of those machines without user needing to type things in. When you're, as a researcher, when you're procuring devices, you should be able to ask for certification that the device will support such a functionality. But as a part of the research communities, we love open standardization processes. And when you look at how the situation is in the world, you have ISO, which is the International Standards Organization, which is even reasonably open standardization process, but the outcomes are, you need to pay for them, but they're good in the industrial world. So if something is ISO standardized, it's usually relatively streamlined in terms of its adoption by the industry. And you can, there are certification processes, and you can get machines, you can get software solutions ISO certified. But the outcome is not completely open, and we still have, so what we have started with Gianluigi and with Jörg was an initiative to do real full-scale ISO standardization of this. And started to look into those components I've already described. So technically solving how to express bundles of provenance that can be opaque, that can sit within one institution, that can be linked together in a non-repudiable way, but still the details of the provenance are only accessible once you're authorized. So not for everybody, only for those, for instance, who are entitled to access personal information at the level of the patients in the given hospital, for instance. We also started to look into the requirements, generic requirements on the provenance information management, so that organizations such as the biobanks or biomolecular resources or even CNRS4 can in the future be certified that you're complying, or we are complying with the requirements on reasonable provenance information management, so that we're actually, we don't not only have the tools how to generate the provenance, but we're actually doing it, and we're storing the provenance in a secure manner. And we need that support for non-repudiation even in the multi-institutional environment. So that was again the example where it was incredible brainstorming with Gianluigi. Hey, there is blockchains. Yes, that would be good, but what is the cost of keeping the blockchain? Do we always need the blockchains? I mean, Gianluigi was very tech savvy, and he loved exploring what you can do as mental experiments with the advanced technologies and how we can drive things forward. So we even have a paper, unfortunately, that was published only after Gianluigi passed away as well. But we have a paper that is already piloting this non-repudiation based either on blockchains or using trusted third parties to implement the provenance in the medical environments, in the environment of hospital information system, for instance. As I already said, we went on an adventure of doing full-scale international standardization using ISO. The standard has been assigned number 23494. It's part of a technical committee on biotechnology and working group on data integration. And we already have a number of parts of this standard, from the requirements on the provenance information management, which is basically the institutional requirements, how to handle the provenance information, development of the common provenance model, which would allow linking those components of provenance together, and then domain-specific standards. So from biological material provenance, data generation provenance, data processing provenance, all the way to things like the database validation provenance, which we even originally haven't thought of, but we were approached by the communities that they're starting to realize we not only need to know how the data was generated, but if they were integrated into a database and the database is then used, for instance, as a part of pharmaceutical industry for validating drug designs, we need to know how the database itself was validated and that it was validated against something else. And we need to have a non-repudiable proof about this. I'll just quickly go through the parts of that standardization effort. So the part one is, as I said, about the requirements on how you manage the provenance, including things like how do you identify provenance information or entities in the provenance information using persistent identifiers, and what are the requirements on their ability to be resolved. How do you find the provenance information and how do you access it and how do you store it and when the provenance information should be generated. The common provenance model, the part two, is handling cross-linking across institutions, opaque components, basics of access control, support or functionality needed for immutability and versioning. That means once you generate provenance information, it should be immutable. You should not be allowed to change it, because then if everybody can change those historical records and at any time, they're no longer, they can't be trusted, because then somebody can just edit things somewhere in the repository and then you don't know what has happened. So basically the idea here is you keep the provenance information immutable, and if you need to fix, for instance, some error, you create a new version of that provenance record and you link it to the previous version so that you can see all the changelog of how the provenance was developing over time. We're also, as a part of the common provenance model, we're also building a repository of commonly used ontologies that are to be used for the common parts of the provenance, not specific for biological material, for instance, but things like authorship information, like units of measurements and error ranges and geocoding support in case that, or geolocalization support in case that you need to comply with Nagoya Protocol, which is a international treaty on return of benefits when using biological material. You need to document the history of the biological material in a way that you can go, if you produce any, for instance, drugs or something as a commercial company, you need to be able to have a trace where the data came from, so that you can return benefits of the biological material that was used back to the source communities. Part three closely follows ISO standards for handling biological material, and it should basically provide technical means how to express all the things that are mandated in those ISO standards for biological material handling in a machine readable way, so that the documentation could be automatically processed. For part four, I've already mentioned OME as one of the examples where communities are thinking, at least, or in case of OME, already implementing provenance within their own ecosystems. And this is happening also in other communities. So for instance, in healthcare, HL7 FHIR standard already specifies at least some basics of provenance for medical records. MPEG-G community, which is standardizing genomic information compression, also works on a standard metadata standard documenting how the data was generated. And other communities are gradually starting to work on these topics. As for the other parts, we're currently working together with University Manchester on using so-called RO crates that have been standardized as Biocompute Standard 2791 in IEEE for documenting computational workflows. And we're looking into the other aspects I've already mentioned. And now I'll show you a domain area which is very close to both CRS4 and my own research group, and which is also being used as one of the pilots of developing this provenance information. And that's digital pathology. And again, we have already seen it in Jason's presentation, and here we will go a little deeper. So what the digital pathology is about, we're trying to use the vast amount of information that is available in the scans of human biological material, namely the histopathological material that is collected either during surgery of tumors or as a part of biopsies when people are going for medical checks, either colonoscopy or prostate, for instance, for men. We can use this biological material, scan it, and use advanced compute technologies to actually identify places where there is potentially cancer or where there is a cancer. And this is a thriving field in the last 5-6 years where different advanced AI techniques are being used. You can use them to either support the diagnosis process, or some are even trying to replace the whole diagnostic process by inferring directly TNM, grading, staging of tumors, Gleason scores, or whatnot. And one of the challenges of this digital pathology field is, of course, there is a lot of papers being published in the last 5 years. But if you look how much is practically used in the clinical practice, it's not that much, surprisingly enough, for several reasons. One thing is to publish a paper that shows nice numbers on some carefully selected data set. The other is to have a system that actually works whenever a clinician applies it, and it produces something meaningful. And even worse, now we have a period of about 2 to 3 years where so-called in vitro diagnostic regulation will come into force. This is a European regulation that poses requirements on clinical tools or things, systems, be it hardware or being software tooling that is used as a part of a clinical practice, how it has to be documented in terms of its development and validation, so that you're not using some obscure tools as a part of clinical process and people are then complaining, why was I treated like this? Well, because the tool told us. And how was the tool validated? Nobody knows. So this is going to have major impact. And the third element is trust of the clinicians in the methods that are being used. I mean, we have in the first presentation that Alfino had, this was the reason, one of the reasons why I asked about if they explored the explainability of the neural networks they work with. Because one thing is that you have a big system with millions of parameters that you're tuning as a part of the neural network. But the other is if you can map it to something physical, or if in this case, if you can make it, if you can map it into biological properties of the material that we know how they work, but we don't know if the network actually sees them that way. Or if it's just a mathematical model that sort of works, but we don't understand why it actually works. And here, what I'm showing in the bottom is actually from a paper that we're about to publish, or it has been actually submitted, that looks into prostate cancer based on supervised learning. So there are annotations that are guiding the whole system, how it's being trained. The system is then providing predictions. But what is interesting here is if you use the explainable AI techniques, in this case, it was based on occlusion, you're able to actually spot the biological features that are really those biological entities that are the decisive entities for the pathologists. So despite they give us very rough guidance, so using those annotations, the AI system trains itself in a way that it really utilizes the biological features that are relevant. And these are things that should be then documented as a part of the provenance. How the system was trained, how it was validated, what are their limits of applicability. And this is one of the reasons why we're using it as a part of piloting that 23494 standard, because it also nicely links all the components together, from the patient to the biopsy or surgery, to the sample processing, to the staining of the sample, to scanning the sample, and to large scale compute analysis of the data. And of course, the annotation generation that is done by the pathologists. So as a way ahead, and these are my last two slides, what I was showing here is an endeavor we started with Gianluigi on trying to practically implement the R of the FAIR and the reproducibility aspects of fair health in a domain-specific and hopefully cost-effective practical mechanisms. Hopefully ending up with a standard that would be both industry accepted and reasonably open, and adopted within large-scale European infrastructures. And here I would like to also express gratitude to Gianluigi, not only for being the partner with whom we brainstormed and worked together, but he has also built a team that is now continuing in this direction at CRS4. So currently it's Luca, it's Francesca, Cecilia, and others who are contributing to this work. Simone, Leo, working with us on the digital pathology. So all of these things have turned into something that actually outlives Gianluigi and continues what he started. So with that, I would like to thank everybody for your attention, and thank Gianluigi for doing the great job with us. If there are any questions, of course, I'm available.
I'll sit here, Petr, just so I don't have to take the mic away from you. So thank you for your talk. Do you have any questions? Do we have any questions remotely? Okay, any questions from the floor? Any questions from the floor? Okay, so something I was wondering, given your choice to go with the ISO standardization process, do you think that could be a hurdle to the adoption of the provenance model within research operations or open source software efforts, things like that, that maybe can't afford the cost of implementing the standard and maintaining it within their own products?
Well, that's a very good question. I mean, the barrier is mostly mental. It's not a real monetary barrier, because what you're paying in case of ISO, what you're paying for is just that you're purchasing the text of the standard itself. It's not royalties or something that you would pay. So the cost is typically something like $30 to $50 for a book that you're buying, basically. and there aren't other costs associated. Of course, what can happen, and we would be heavily pushing to avoid this happening, is that that somebody claims some royalties based on patents for this kind of work. But ISO has an internal mechanism how to do review of existing patents, and you can avoid those royalty, or you are at least aware that there are those royalty fees. So if you look, for instance, at JPEG 2000 standard, which is an image compression standard, part 1 of JPEG 2000 is royalty free, while the other parts may be encumbered with royalties. So in this case, we believe there is no patent issues, and there will be this screening process happening before publishing the standard as well. So the aim is to avoid any royalty fees, and the implementation in the open source software would be basically only for those who are developing it, only to buy the standard. And ideally, what we would like to get is this standard is open for everybody. We know that there were some precedents like this even in ISO. So there were some standards that were published also as open standard. So we're investigating that path together with ISO Secretariat so that it would be completely cost-free. But of course, ISO has also their established ways of their established business model, which is based on selling those books, so to say.
Okay. Okay, thank you, Petr. Thank you very much. Okay, so on to our final speaker of this session. Our third speaker is Francesco Marroso. Francesco is a retired professor of neurology at the University of Cagliari and a retired neurologist at the hospital in Monserrato, the Politecnico Universitario di Monserrato. He is an expert in epilepsy, neurophysiology of sleep, and neurodegenerative diseases. And today he's going to be presenting a talk entitled Electroencephalographic Signals in Pharmacoresistant Epilepsy After Vagus Nerve Stimulation Treatment, a computational approach. Thank you, Francesco.
Thank you very much, and thank you for inviting me to this meeting. And my talk falls apart from the general stream of this meeting, since I'm a clinician, and I met Gianluigi in 1994 when both of us were from an experience in the United States, and exactly in the same place, but we are unaware one of the other, of course. Gianluigi was very interested in bioelectrical signals, and his interest focused on EEG, digital EEG, which was a really turning point then, because EEG, electroencephalogram, was done with an analogic method, and give rise to a sheet of paper, and you can see several alterations on whatever, and then all things were dead right away. Instead, with the digital signal, with Gianluigi, we thought that at time we can do a lot of things. I mean, interrogating the digital signal and doing other things. Okay, so next. Is this? Okay. And so this is a quip from a famous neuroscientist, which is quite opportune in this talk. And to be continuing the penultimate slide, I say. Science evolved because some unknown aspect frequently is unveiled, not only as the consequence of the application of new technologies and blah, blah. The ultimate slide is quite appropriate for the Gianluigi's influence in this kind of research. So I illustrate this technique, which is named the vagus nerve stimulation, and most of my talk is in order to make a passage from the microenvironment of the reason of this practice to the meso micro scale, which we explored with Gianluigi and his associate Federico Santoni in primis. And because it is really the most important thing in interpreting vagus nerve stimulation effects. So what is vagus nerve stimulation? First of all, this is a practice which is applied to epilepsy. Epilepsy is really excruciating problem, and because about eight person every 1,000 is affected by epilepsy, so it's going to be the second or third disease in order of importance in neurology. But there is a very serious fact to point out, and is that 30% of all epileptic patients are unable to receive benefits from pharmacological treatment. And then there is a rush for trying other solution, and this is one of the most brilliant, the vagus nerve stimulation, which has been discovered serendipitously by this person, Zabara. As a matter of fact, he was thinking about his dog. The poor beast was epileptic, and he thought about all the researcher in stimulation of the vagus nerve, and they came up to the solution of a big device. Actually, the first device were so big, and it was implanted, and the device was implanted like a cardiac pacemaker with a connection tunneled directed to the vagus nerve. And the vagus nerve is a pretty interesting nerve. It's a chronic nerve, but it's termed vagus because it means the wandering nerve. The vagus nerve has connection with mesenteric structure, with the cardiac structure, and so on. So the most important part for us is that the target of the vagus nerve, of the afferents, is the dorsal raphe nuclei, locus ceruleus, amygdala, hypothalamus, thalamus, and orbitofrontal cortex. Now, the brain is a pretty strange structure because a small part of the brain play a role of the what you call hub. I mean, there is a strong influence of a very small part on the total dynamic of the brain. And one of these is the dorsal raphe nuclei and the locus ceruleus, regions which receive inputs from the nucleus, the tractus solitarius, which is the main afferents of the vagus nerve. So Here is the reason of the stimulation of the vagus, because the structure exerts a kind of regulation, and among this regulation, very important is the anti-epileptic function. I refuse to comment on all this. Anyway, you see the vagus nerve is a major component of the autonomic nervous system, and maintain the homeostasis and other things. Left and right usually are a different target in the cardiac target, which is important because the stimulation of the cardiac nerves are a byproduct not pleasant sometimes to this practice, but there is no reason to halt surgery, an implant of the vagus device for this, because there is no big problems actually. The technique is surgical technique, is considered a low-level surgery, and is basically the same technique that is very used in cardiology. It's like a pacemaker with a connection with the nerve. The generator is programmed by a wand, which can regulate the intensity and all this. This is a short putative consideration on the target of the vagus nerve, which is this point. Okay, this is the nucleus, the tractus solitarius, and this is a kind of of belt from this, which involves more or less all the brain, and this is a consideration we thought was interesting for other things. And I shortly will illustrate several of this fallout of this practice, because vagus nerve stimulations now are lot of different application, and some discussion with Gianluigi fueled our intensity of research, basic research, before to perform the EEG study. This is, of course, the locus coeruleus, which is a very small structure in the brainstem, and this structure is involved in a very important function. One is to lower the intensity of epilepsy, or the fits, the epileptic episode, anyway, the seizures. Okay. Because there is a mediation of this substance, which is noradrenaline, and noradrenaline in epileptic models of animals, if is lowered, then increase the intensity of epilepsy. If it is increased, then the epilepsy, the mechanical stimulation or whatever are less intense. However, the use of VNS led to the consideration that this substance, non-epinephrine or noradrenaline, is also very important in other functions. And okay, this is a model which showed that the seizure induced by pilocarpine is lowered by the increase of stimulation of adrenoceptor and with epinephrine. This is, I'm sorry, this is in Italian, but I can quickly translate. This is a research we did, and this research shows in rats that the stimulation increases the noradrenaline in particular areas. The prefrontal area is one of the most targeted areas in psychiatry, since an antidepressant, the venlafaxine, antidepressant give the same peak, see, the same peak that the vagus nerve stimulation of norepinephrine. This is extremely interesting because the same year or 1 year after this paper, the Food and Drug Administration, the American Food and Drug Administration, allowed the market of vagus nerve stimulation as antidepressant. So in cases very resistant to drugs, this device has been suggested to be effective in depression. And it's the same happened with the serotonin. As you know, the serotonin is the latest target of antidepressant, because the Prozac and the other drugs are today the most used, and in substitution of the tricyclic antidepressant drugs. Okay, this I already said. The other thing is that the interest of this implant is reverberated by the activity in the increase on the modulation of the substance, which is the GABA, amino acid gamma butyric acid, which is a big modulator of the inhibition in the brain, and which is the controller of the semi-chaotic signal of the EEG. The GABA lowered the intensity of the chaos of the activity, the EEG activity. This paper indicates a very interesting thing. See, this is a patient who underwent vagus nerve stimulation, and this is the pre-vagus implant. You see on the left how the injection of ACD, which is acetylcysteine dimer, which tests how the circulation in the brain is good. So, because if the circulation isn't good, you can perform the rest of the experiment. In this patient, the circulation is pretty good. In the right, you see the injection of yomazenil, which marks the GABA competence. You see a large breach here, after vagus nerve, you see that breach was no longer in place. Okay, same circulation is okay, and so you see this plasticity of the vagus nerve stimulation. Why I'm talking about these things? Because talk about the paper, the work with Gianluigi, because all this kind of modification are the micro scale telling images of the macro scale events represented by the EEG signals, by the activity of the electrical activity of the brain. And interesting enough is this. This is in a patient, in a non-responder patient. As you see, same, you know, the circulation is okay, but you see the breach remain the same after 1 year. So the plasticity is directly consequence of this practice. This is and this paper shows another thing. We did we tested the plasticity with another component, which is the neuro it's like the factor of the factor of growth, the growth factor of Levi-Montalcini, and this factor is the BNF, which is an expression of the plasticity of the brain in this area. As you see, in the shame operated, the BDNF and the BFGF, which is another analog, C is exactly this, and after VNS is this. And this test with the cyclophilin shows that the competence of the system, there is no other alteration than the plasticity. You see this. Okay. Okay, this is a study by Simeonato, which shows the rule of the BDNF, and the article was entitled Angel or Devil, because the BNF, if it's mature, performs a particular effect. If not, then there is epileptogenic. Okay. And one crucial hub for epilepsy is the hippocampus. The hippocampus is extremely interesting. As I don't know if you are familiar with this structure, because in 2014 the researchers on the hippocampus received the Nobel Prize because the hippocampus is the place where the memory is set, and is the main culprit of the Alzheimer's disease if lesioned. Okay. So it's important to see what happened in the hippocampus. And all in all, it's a place where epilepsy is very active. The epileptic brain, most of the time, in partial or focal epilepsy, the epilepsy starts exactly from this structure, which has a particular brain, a particular electroencephalographic activity, which is prone of being intercepted by synchronization and then epilepsy. This is okay. This is what we we found. We found that VNS induce an increase in this kind of, you know, the prolongation of the axonal pathways if compared with the sham operated. And most interesting is this slide, because the sham operated is this one, and this is the hippocampus after a BDNF, and this is an increase in the cell population. So there is a neuronal increase of population, so there is a plasticity, and there is an increase in neuronal cell, because this system shows the neural cell and the glial cells. This is these are neuronal cells. Also, cardiovascular effects are induced by VNS, and this is the heart rate, and this is, I'm sorry that the color are not the most, anyway. This is the increase in the differentiation in heart rate variability. Okay, and this is without VNS. Sorry, this is okay, this fact is not trivial, because if you modify the heart rate, you decrease the occurrence of death in epilepsy, which is 17 times more frequent than in other pathologies. Okay, in other similar pathology, neurological pathologies. Okay. Oh, this is another very interesting consequence, the weight loss. See, we did this with metabolic cages, and you see the shame operated, you see the fat, and there is almost 1/3, maybe less than the fat you see here. This is done with a very interesting strain of rats, the Zucker rats. A rat Zucker was the one in Cinderella, I think, the fat rat. It's a Zucker. Oh, also the tremor. This is very interesting, because the tremor in multiple sclerosis is very impairing condition, and VNS is able to decrease. After this, back to Gianluigi. We looked at the digital recordings in 11 epileptic subjects, and we see that if you apply mathematical division, like mathematical windows to the signal, and we made the signal stationary instead of dynamic. So this is a limitation, but there is no way for this. And we examined the digital signal after VNS in subject improved after VNS. So we see this, an increase in 20-50 Hz gamma frequency, and synchronization after chronic nerve stimulation. 20-50 Hz are a frequency which contrasts the epileptic synchronization, because the epileptic synchronization is better performed by frequency very slow, because slow frequency tend to synchronize more easily. And so VNS decreases the synchronization of theta frequency, which are frequency slower than around 4/6.5 Hz. And where it increases gamma power spectrum and synchronization. This is our finding, and we see that this reduction was directly correlated with the anticonvulsant effects. It's interesting, the second, in addition, gamma modulation could also play a seizure-independent role in improving attentional performance, because attentional performance is probably are modulated by the increase in noradrenaline, norepinephrine, which previously I showed in rats. This more or less is the same principle. And this work set the stage for a very recent paper we did with bioengineers, looking at the reorganization of functional brain networks in pharmacoresistant epilepsy who responded to VNS, the same principle. And this is a very short resume the results. It is the minimal spanning tree, which is examined, the minimal spanning tree, and we see that the leaf is increased, okay, in responder, see the non-responder, and this the diameter is decreased, which means the health, the robustness of the network, and this is the reactivity. You see the same, and you see the result in the hierarchy. Okay, that's it. The conclusion and the quip is by François Jacob, and he say, but also for a novel way to exploit and to share previously point of view. So Gianluigi was really a specialist for inseminating ideas and new possibilities, and for this and for other things, but for this we lost a friend and also a precious advisor. Thank you for your attention.
Thank you, Francesco. Any questions from the floor? Remotely? No, okay.
Pretty tired.
That's the disadvantage of being the last speaker. But so I was wondering one thing, vagus nerve stimulation, seeing how many effects that it has. Is it approved for use in Europe as a therapeutic method? And how commonly is it used?
Sorry,
how commonly is it used? How frequently?
Okay, it's very common actually. I think that to date, maybe all over the world, at least 200,000 implants were already in place. Consider that the implant is costly, so you should weigh benefits and cost. But it is interesting that same paper from third world countries say that is advantageous also in these countries because the number of seizures are diminished consistently after VNS. So you can imagine the admittance in a hospital because of this kind of patients need hospital wards of neurology, of intensive care unit also for a lot of time, also 2, 3, 4, 5 times a year. Okay, yeah.
Okay. Thank you then. Let's thank Francesco again.
Okay, I just want to thank everybody for the morning. I want to thank the speakers and the public here, and also the people that are connected. We have had from 50 to 60 persons constantly connected overall all the time. Now the morning is closed, so we close the part dedicated to scientific talks, but the day is not finished. In the afternoon, we will have another session of smaller time talks on the technological and application parts of the work that was stimulated by Gianluigi or done by Gianluigi. And then we end the day with a more personal part. In the afternoon, as I said, the talks will be in Italian, and also the personal memories part will mostly be in Italian. But we will be also connected over the internet for everybody. Now we can just go around the city, we'll do whatever, and we reconvene here at 3 o'clock for the afternoon session. Thanks again.